I'd like to welcome everyone to this session where we're going to discuss various different ways of probing the absolute mass scale of the neutrino. Thanks to everyone who's here in person and everyone who's here online. And our first speaker is Dr. Christine Klessens from the University of Washington. I'll try to move the video.
All right, should I start?
Yes, sorry, please go ahead.
Okay, well, thank you first of all for the invitation and the opportunity to talk in this session. So I'm going to talk about how the neutrino mass can be inferred from beta decay and electron capture kinematics in general, and give an overview over current experiments in this field. And I want to begin with a very brief reminder that since neutrinos are massless in a standard model, neutrino masses themselves are new physics. And we know from the observation of neutrino oscillations that at least 2 of the 3 mass eigenstates are massive, but we have not been able to measure the masses yet because they are so light, which poses the question why that is. And the standard model, the minimal standard model doesn't really explain this, and therefore an extension is required. There's a number of other open questions about the neutrino, namely whether M1 or M3 is the lightest neutrino state, whether they are Dirac or Majorana fermions, and whether this way they participate in lepton number violating processes like neutrinoless double beta decay, and whether they are sterile neutrinos. And all of these questions are related to the neutrino mass and can be informed to some extent, at least by measuring its magnitude. So there are several ways in which the neutrino mass can be probed, each of which is sensitive to a different quantity, and we will hear about all that are sensitive to the absolute mass in this session. So not sensitive to the absolute mass are, where's my cursor, neutrino oscillations. Here the survival probability is proportional to the mass squared difference. So neutrino oscillations inform us about the mass differences, but not about the absolute scale, and also not about all of the signs, which is why we're left with this question about ordering. Cosmology is sensitive to the sum of the mass eigenstate and has given us the most stringent limits so far. However, these limits are model dependent, and the most direct way of measuring the masses would therefore be a kinetic determination in beta decays or electron capture, or in neutrinoless double beta decay, a process that is only allowed if neutrinos are of Majorana nature. So to extract the neutrino mass from beta decay or electron capture, we look for the shape distortion that they induce near the high energy endpoint of the spectrum, because here the impact is largest. Decay experiments are sensitive to the incoherent sum of the mass eigenstates, which can be considered an effective mass. And this method is complementary to the other mass inferring methods in that it is independent of cosmological models and of the nature of neutrinos. So we are looking at completely different systematics here. The requirements for a suitable isotope for this measurement are listed down here. So you want an isotope with a short half-life and a low endpoint, because that maximizes the statistical power near the endpoint. But you also need a spectrum that is very well understood and can be precisely described theoretically. And the 2 most promising candidates that are currently being pursued are tritium beta decay and holmium electron capture. So here are the decay spectra of tritium and holmium. And this is a zoom into the on the endpoint region and what the distortion would look like for a 1 eV effective mass. So the spectral shape near the endpoint is largely given by the phase space factor that is reduced by the emitted neutrino mass. And in reality, the total decay spectrum is the incoherent sum of the spectra from all individual masses. So with sufficient sensitivity, you could resolve the individual masses. But as long as the masses are not too small, they can be summarized to this effective mass. And then the spectrum can be approximated by this expression here, where the phase space is a single factor reduced by only the effective mass. And then for limiting or measuring the effective mass, the task then becomes to record a decay spectrum with high precision and fit the endpoint region with this model. So one experiment that is currently doing that very successfully is the Catwin experiment. Here, electrons are emitted from molecular tritium decay in the Swindler's gaseous tritium source, and then they are guided magnetically to the main spectrometer. And on the way to the main spectrometer, the magnetic field decreases slowly but drastically, which aligns the momenta of the electrons with the electric field, and then only electrons above a certain kinetic energy make it across the electrostatic retarding potential and are then counted by the segmented detector in the end. So Katrin started data taking in 2019 and has so far published the results from 2 data taking campaigns. In each campaign, they scanned the retarding potential across the endpoint region, and this way they recorded an integrated spectrum. And by combining the results from the 2 campaigns, they have set an upper limit of 0.8 EV at 90% confidence. Katrin has also set a limit on relic neutrinos by looking for neutrino capture events in their data. If a relic neutrino is captured by a tritium atom, an electron with an energy higher than the endpoint energy is released. And while Katrin is not sensitive to the expected average neutrino density in the universe, they have set limits on a local overdensity of 10 to the 11 and will further decrease this limit with more runtime to come. So one issue that Katrin had in the past few years was that the background was larger than what was initially planned. But in the meantime, Katrin has managed to eliminate a lot of the uncertainty related to background and the source potential. And this plot shows here how significant that reduction is compared to the first 2 campaigns. So we can look forward to new limits in the very near future because another round of unblinding is already planned for this year. Eventually, Katrin will reach its design sensitivity of 0.2 eV, and at this point either measure the mass or set a new limit that is a full order of magnitude below the limit set by previous decay experiments. Okay, so here's another way of looking at the Katrin sensitivity. It's shown here in shaded green on this plot of the effective mass versus the sum mass eigenstates, which is what cosmology is sensitive to. And the question for the future that now arises is how can we go below the Katrin limit with laboratory measurements? Well, the first thing that we have to do is we have to accumulate more statistics. And because the sensitivity scales with the number of observed decays to the power of a quarter, that is not an easy task. So if you look at the Katrin experiment, increasing the source density or the size is not feasible because the experiment is already really large, and also if you increase the source density, you increase systematic uncertainties. And then also if you want to go below 0.1 EV, you will be limited by the width and uncertainty of the molecular ground state. So if you want to go below that, you have to do experiment with atomic tritium where the ground state is a lot more narrow. So we have to find a way to do atomic experiments to go below that. So one experiment that wants to do an atomic tritium measurement is the Project 8 experiment. Project 8, for this purpose, has developed cyclotron radiation emission spectroscopy. The working principle of this technique is to place the tritium source gas in a strong homogeneous magnetic field, and then also trap the emitted electrons from the decays in a magnetic trap. The electrons emitted in the decays will then emit cyclotron radiation, and that radiation can then be detected with an antenna or a cavity. So here's what a typical crash signal looks like if you do Fourier transforms and plot the power versus frequency and time. And you can see that while the electron is trapped, it emits narrowband radiation, and due to radiative energy loss and because of the energy loss from scattering with gas molecules, the frequency slowly rises, slowly for the radiative loss and quickly for the scattering. The frequency rises because in the relativistic regime, the frequency is proportional to 1 over the energy. So to reconstruct a decay spectrum from these signals, you have to identify the starting point of all these events, because only here the frequency corresponds directly to the energy after the decay. In the prototype phase 2 of Project 8, the collaboration has recorded the first molecular tritium spectrum with the CREST technique. And the detection of cyclotron radiation was accomplished here with a waveguide setup where krypton or tritium gas was built into a waveguide cell inside a 1 Tesla magnet. And by using a shallow magnetic trap, the Project A collaboration has demonstrated an energy resolution of 1.7 eV for the krypton K line. For the tritium data taking, Project A used a deeper magnetic trap to increase the statistics at the cost of energy resolution. So here's the first tritium spectrum that was recorded with this technique. And here are the results from analyzing this data. So the endpoint is at 1 sigma distance to the literature value, and neutrino mass limits of 178 and 169 EV were set for frequentist and Bayesian analysis respectively. And one thing to point out is that there were no events recorded beyond the endpoint, which sets a limit of 3 times 10 to the minus 10 per EV per second on the background rate of this technique. So a major selling point of CRESS is that it is compatible with atomic tritium, because the electrons are detected by the emitted radiation, and the source gas and the source is transparent to this radiation. There's no need to extract the electrons from the source. So this makes it compatible with atomic tritium, because in order to prevent the atoms from recombining, they have to be isolated from the vessel walls. And this can be achieved by magnetically trapping them by coupling to the spin of the unpaired electron. And if you trap the atoms magnetically, it becomes impossible to extract the electrons from the source, but with CRESS, there's no need to. Other advantages besides the atomic tritium compatibility are, as I mentioned, the low background rate, which increases the sensitivity near the endpoint, but also that frequency measurements are inherently very precise, which gives this an excellent energy resolution. And because CRESS records a differential spectrum, you can observe the entire endpoint region at once and don't need to scan the potential across the endpoint. So if this experiment can be run with larger volume, it is a great candidate for achieving below 0.1 EV sensitivity. And here is the experimental concept for the future of Project 8. It all begins with an atomic tritium source where molecules are split into atoms. Then the atoms are guided, cooled to millikelvin and guided magnetically to this volume here. And this volume is inside, is a magnetogravitational trap, and is inside a magnetic field. And the emitted radiation from the electrons is then picked up by a cavity. And with this concept, Project 8 plans to reach a final sensitivity of 14 electron volt. Okay, so because I have been talking about sensitivity a lot, I want to do a quick excursion to how sensitivity can be easily estimated. And then after that, I will get to the electron capture experiments. So there's a simple analytic way of deriving the sensitivity, which is shown in this report by Formaggio, De Guva, and Robertson. And I'm just briefly summarizing the results here for the example of a differential tritium decay measurement. So it's all based on the fact that the neutrino mass reduces the number of counts in the endpoint region for a given energy interval delta E. And the number of signal events and background events is given by these two expressions here, where the branching ratio, where R is the branching ratio to delta E for a zero neutrino mass, B is the background rate, and T is the measurement duration. And one can then obtain the statistical uncertainty on the neutrino mass from the standard deviation of the total number of events in delta E, which gives this expression here. And then the systematic uncertainty results from all contributions to the energy resolution and their uncertainties delta E. So for a tritium decay experiment, these energy resolution contributions are usually the instrumental resolution, which depends on your measurement technique, the thermal Doppler broadening from non-zero gas temperature, and the width and uncertainty of the final state spectrum. So combining, you can combine the statistical and systematic uncertainty to create a plot like this. So here the standard deviation on the squared neutrino mass is here on this axis, and the 90% upper limit that you could set is on this axis. And here the sensitivity is plotted versus the total exposure given as volume times efficiency times time. So when you look at this plot, you can see right away what you have to do in order to improve your sensitivity. To move downward on this plot, you have to reduce your background and or improve your energy resolution. And to move to the right on the curves, you have to increase your statistics, which you can do by increasing or improving any of these three quantities. The plot also shows how the sensitivity of molecular tritium in blue is limited because of the finite state spectrum. And if you want to go lower than that, you have to switch curve and use atomic tritium. Yeah, so that was just a quick excursion to sensitivity. Now I want to switch gear and talk about the electron capture experiments. As I mentioned before, the current experiments measure electron capture on holmium decays, which is advantageous because holmium has a very low endpoint. Holmium decays to an excited dysprosium atom, which then undergoes subsequent decay to de-excite. In principle, the neutrino mass measurement here works the same way as for tritium, in that the mass can be extracted or limited by a shape analysis of the endpoint region. In order to do that, the spectral shape has to be known very precisely, and high resolution measurements by the ECHO and the NUMEX experiment have shown that the spectrum shape is more complex than what was initially thought. But in the meantime, the theory has caught up a lot and the description of the spectrum could be much improved. And it was also shown that the endpoint region is smooth and exponential, and it is dominated by the phase space vector. ECHO and the Holmes experiment are measuring holmium decay spectra by implanting holmium into the absorber material of microcalorimeter pixels that measure the temperature increase from the released de-excitation energy. The microcalorimeters of the Holmes experiment are transition edge sensors, where a small change in temperature leads to a large change in resistance. And in ECHO, the temperature change is measured from the change of magnetization of the detector material. With an array of 4 of these microcalorimeter pixels, ECHO has recently set its first neutrino mass limit of 150 eV. And they've also done an endpoint measurement that is awaiting cross-check with new panning trap measurements. This was possible due to an improved theoretical description of the decay spectrum. And now the holmium experiments are heading towards sub-eV sensitivity, which will require to observe 10 to the 14 decays near the endpoint, a low background rate, and an energy resolution better than 3 eV. And this plot here shows the sensitivity that could be achieved by these experiments depending on the pile-up rate. So the pile-up rate is given by how often you have a decay happening in a pixel where the previous decay hasn't been fully read out yet and the temperature hasn't gone back to the baseline temperature. So the pile-up rate has to be kept low, and this limits how much material can be implanted in each pixel, and therefore a large number of pixels is required. And to be able to read out arrays with many pixels, both collaborations are working on a multiplexing readout, and both have demonstrated that successfully that this is possible already with a small array. So we can look forward to lower and lower mass limits of these experiments. So now the last experiment I want to talk about is the Ptolemy experiment. I've shown you earlier that decay measurements like Catcher can set limits on the radic neutrino overdensity. And radic neutrinos originate from just 1 second after the Big Bang, and they carry interesting information about the evolution of the universe. So the Ptolemy experiment is going for a direct detection of radic neutrinos by looking for a peak beyond the endpoint of the tritium beta decay spectrum. To do this, they will need a large amount of tritium and an excellent energy resolution. And if they can achieve this, they will also be sensitive to the ordering, because the spectral shape at this resolution is depends on the mass ordering. And they will also be sensitive to the absolute mass scale. So here's the experimental concept. They want to implant tritium on a graphene substrate, and then the decay electrons leave the surface of the substrate and are detected with RF methods, as is done by Project 8. Then afterwards, the low energy electrons are filtered by a transverse drift filter, and the high energy electrons are slowed down. and their energy is then determined by transition edge sensors. The target energy resolution here is 50 millectron-volt, and the development of the demonstrator is ongoing, and the ultimate goal for this demonstrator is to use hundreds of micrograms of tritium and measure electrons with a resolution of 50 to 100 milli-electron-volt. And this is planned to happen on a timescale of 5 years. So an experiment like this, as I said, would also be sensitive to the absolute mass scale. And in this plot, you can see the mass resolution that could be achieved depending on the energy resolution and the mass of the lightest neutrino. Okay, so this brings me to my summary. Neutrino mass measurements from decay kinematics are a direct and model-independent approach that is complementary to the systematics in cosmological limits and can give us clues about beyond standard model physics. And in a few years, Katrin will find the mass also at the limit of 200 millectron-volts. And in the meantime, crest-based tritium decay and bolometric holmium decay experiments are moving towards EV scale sensitivities. And then on the longer time scale, these experiments want to reach sub-EV sensitivities down to 40 millectron-volts. And the Ptolemy experiment even wants to reach a sensitivity that allows them to detect relic neutrinos. Yeah, and with that, I want to thank you for your attention.
Well, thank you very much. We have several minutes for questions. If you are with us on Zoom, please raise your hand to signal that you have a question or questions in the room. So far, it looks like your talk was very clear. I was wondering if you showed a beautiful first tritium spectrum for Project 8. And I was wondering if you could talk a little bit more about why the spectrum has the shape that it does.
Yeah, so the shape here is, well, it's the basic tritium shape that we know, convolved with the detector response and then multiplied with the detection efficiency. And the detection efficiency has a strong frequency dependence in this experiment. And therefore you have a distortion of the tritium spectrum shape here, which is very well understood though from all the systematic studies that were done. So for example, this kink here, at this frequency, there was a resonance in this experiment where just the properties of the events at this point were very different, and therefore the detection efficiency from the offline reconstruction methods was reduced, and therefore there is this kink here in the spectrum. And then overall, because of high-pass filters, the efficiency decreases towards lower energies here, because lower energies are higher frequencies. Low pass filters, sorry, I got it wrong. So the low pass filters decrease the efficiency here on this side. Yeah, so this method, like tritium decay experiments or all spectrum shape analyses, have to know whether their efficiency across the energy range they're analyzing is constant, and if it's not constant, then they have to study the shape in great detail of the efficiency, otherwise this introduces additional systematic uncertainties.
Thank you very much. The next question is from Massimiliano Latanzi.
Yeah, thanks. So first of all, thanks, Christine, for the very interesting and clear talk. I have a question about the time scale for Project 8, in the sense, is there any, again, time expectation for when the 40 MeV sensitivity will be reached?
Yeah, that's a good question. There are plans for atomic tritium demonstrators or demonstrators that want to show that this experimental concept works on a several-year time scale, so maybe order 5 years, 3 to 5 years maybe. But then for the final experiment, it's definitely a longer time scale, because this will be a large experiment, and the collaboration is still like studying all the aspects of it. So I could, yeah, I don't think I can give you a precise time estimate, but it's definitely on the 10 years or more time scale.
Okay, thanks. Sorry, when you say 3-5 years, you mean of integration time? So you mean or it's 3-5 years for what? Sorry, I didn't get what 3-5 years referred to.
For design studies and test experiments.
Okay, got it, sorry. Thanks.
Right. Thanks. Our next question is from Hamish Robertson.
Yeah, thanks, Christine, for this nice talk. The Ptolemy experiment, I believe, is using this graphene source, and there are papers that say that the 0-point motion of the tritium bound to the graphene will create line broadening that is much larger than is shown, for example, in the slide you were just showing. That's the next one after, maybe the one before that. Yeah, there. Do you know how they will get around that?
I don't exactly. I know that they are doing studies of how much this peak here overlaps depending on energy resolution and with and other width uncertainties. So they have this paper where they study the sensitivity for different amounts of overlap of these two parts of the spectra. But I am unfortunately not familiar with their exact strategy for how to cope with it. I just know, yeah, their sensitivity is impacted by it to some extent, and they are studying the overlaps.
Yeah, okay.
I can comment a little bit from the room. This is Diana Parno, that I recently saw a preprint where they're experimenting with other geometries of the substrate. So it looks like I think what they had settled on in this theoretical study was that a more or less free tritium atom moving inside a hydrogenated carbon nanotube wouldn't suffer from these final state effects that broaden it, but there are obviously technical challenges that they would need to overcome.
Yeah, right, thank you.
Can I ask a related question while we're on Ptolemy?
Yeah, so
there was a statement that they have a demonstrator coming in like the 5-year time scale. How many pieces of technology, Ptolemy technology, are in that demonstrator? Do we know? Does anybody in the room know? I don't know if Christine knows, but is it like the graphene carpet of tritium, the RF detection, and the transition edge sensor calorimeters? Is it all of that or just parts of that?
I think I saw a Ptolemy talk yesterday where they described this as a full-scale prototype, and
So
that was supposed to include all of the pieces, but I think like the magnets would be normal conducting, not superconducting. I didn't catch enough detail to answer your question. Christine, do you know, or anyone else online?
No, I don't know more than what you just said. So on the Neutrino conference, they also presented the 5-year timescale for the demonstrator, and yeah, I think it's an ambitious timescale, but they are working on every part of the experimental concept, and they do plan to have a full working demonstrator on that timescale.
Okay, another question from the room.
I apologize if you covered this, but are there other approaches under discussion besides Ptolemy? Anyone else?
For relic neutrinos?
Yeah.
Christine?
Not that I'm aware of. I mean, every tritium decay, or every neutrino mass decay experiment has, well, if it had enough statistics and resolution, could, every experiment can set limits to some extent, but you just need a huge amount of tritium to be sensitive to relic neutrinos. And I'm not aware of another experiment other than Ptolemy that is currently planning on doing that.
Thank you.
All right, thanks. So thank you again, Christine, for an excellent talk. I'd like to close this discussion, but we'll have more time for discussion at the end of the break. Next up, we'd like to hear from Eleonora Di Valentino. Dr. Di Valentino is going to tell us about neutrino mass from cosmological probes to give us an alternative observable. Can you share your slides?
Hello. Yes. Okay. Can you see my slides now?
Yes. Okay, and they're beautiful, full screen. We hear you well. Please go ahead.
Okay, perfect. So let me see. No, okay, that's the mouse. Okay, so thanks a lot for the invitation, first of all. And today I'll talk about how to constrain the neutrino mass using cosmological probes. So neutrinos are the only particles in the standard model. Last particles whose masses are still unknown. And to measure the total neutrino mass with the cosmological data, we depend on the creation of the cosmic neutrino background at the early times and the growth structure late times. So in order to measure this mass, we want to use the cosmic microwave background and the large scale structure data. So as everybody knows, the CMB, the cosmic microwave background, is the radiation emitted at recombination, where the photons have the scattering. And okay, this radiation occurs with the expansion of the universe, keeping the body spectrum of the primordial plasma with which photons were in thermodynamic equilibrium. And today we measure a body spectrum at a temperature of about 2.73 Kelvin. So on this black body spectrum, there are small anisotropies of the order of 10 to the -5, and we can expand the Legendre polynomial, the 2-point correlation function between the difference of temperature and the direction in the sky. And this way we obtain the temperature power spectrum. Now what we do is to assume a model that is specified by a number of parameters, and we vary these parameters and we compute the theoretical expectation for the temperature power spectrum. And we see that varying different parameters, we have a similar effect on the observable. So now what we want to do is to find the best combination for the parameters that can fit the data, and we do this using a Bayesian analysis. So usually MC codes. So the model that we assume is a lambda Gaussian matter model that has just 6 parameters, but we can introduce additional parameters in the neutrino sector, like the total neutrino mass, but also the neutrino effective number. And this way we have the constraints at 95% confidence limit on the total neutrino mass. So we expect also to have a cosmic neutrino background in analogy to the cosmic microwave background. So neutrinos are in thermodynamic equilibrium with the primordial plasma using through the weak interactions. So when the rate of the weak interaction falls below the expansion rate of the universe, neutrino decouple, and this happens at a temperature of about 1 MeV. But photons are still heated by the electron-positrons annihilation. Then when also photons decouple, we can compute the ratio between the temperature of the two backgrounds, and that in approximation of an instantaneous neutrino decoupling is equal to this quantity. So today we expect a cosmic neutrino background at a temperature of about 2 Kelvin. That has not been directly detected yet, but we have indication indirectly by the measurement of the neutrino effective number that is actually measured at more than 10-15 sigma, different from 0. So neutrinos are the only particles in the standard model to have a transition between the relativistic to the relativistic regime. When they are relativistic, will contribute to the radiation content of the universe, and when they become relativistic, will behave like matter. So like baryons and cold dark matter will contribute to the expansion of the universe like in this way. But the point is that their velocities is not negligible. Say they don't fall below the gravitational wells of the dark matter, and so they cluster only at scales larger than the Infraschini scale. This is the reason why they affect the large scale structure. So if since the CMB spectrum is mainly related to the physical evolution before recombination, having a different neutrino mass different from 0 is affecting the CMB through a modified background evolution, some secondary anisotropic correction. So when we vary the total neutrino mass, we are changing the matter to radiation equality, and we are changing the amount of matter density today. This is the effect that we expect on the temperature on the CMB in general. So we will have a changing of the position and the amplitude of the peaks, and we also have an effect for the ISW the early ISW and late ISW. And then we have an effect due to the damping tail, in the damping tail to do the lensing. So if we use a CMB data to constrain the total neutrino mass, and in this case we're using Planck 2018, so the last release of Planck, we see that the upper bound is less than 0.26 eV and 95% confidence level. So this is very strong. But if we have a measurement of the CMB, we know that the CMB is formed at a temperature of about 0.3 eV. So this kind of particles are still relativistic at recombination. So how can we obtain these amazing upper limits? And that's because we have a measurement of the gravitational lensing. So photons coming from the recombination are deflected, the path is deflected along the line of sight because of the massive structure in between. So that effect can be measured in the damping tail of the temperature power spectrum. And that's if we have such a stronger limits on the total neutrino mass, this is a clear indication that we are detecting this gravitational lensing. Okay, actually, okay, if we have massive neutrinos, that means that we have less structure. Less structure means less lensing. So if we have a smaller neutrino mass, that means that we have a stronger lensing measured by the CMB. So the fact that actually, okay, we are just, if we have massive neutrinos, we are in some way affecting the structure formation of the universe, means that we can use the largest scale structure data to measure the total neutrino mass. And the main large scale structure observables are the power spectrum of the non-relativistic matter configurations in Fourier space and the 2-point correlation function in the configuration space. So regarding the matter power spectrum, this is the effect we expect varying the total neutrino mass. So we see this suppression at small scales, high Wood numbers, and we can use a different observable to map this matter power spectrum. We have the gravitational lensing of the CMB in the linear regime, and then we have the clustering and the weak lensing of galaxies, and then the cluster number counts, the number density of galaxy cluster, and these are the Maldry and nonlinear regime. So, okay, we can in this way map the whole matter power spectrum, but we can have problems because, okay, we don't know really well how to handle with the non-relativistic regime, and we have to use n-body simulations, and or because the perturbation theory can be used just in the Maldry nonlinear regime. So these are really difficult to measure to do and be used. But then we have also the BAO data, the baryon acoustic oscillations that are formed in the early universe because the gravitational collapse is counterbalanced by the radiation pressure. So until the drag epoch, then it is when photons and baryons decouple. So this scale is imprinted in the CMB, but also in the local structure. So when we compute the 2-point correlation function in the configuration space for the galaxy, we see that we have this peak. This is really sensitive to the total neutrino mass. So these are the different BAO probes that we can measure different redshifts, and combining now the CMB data with this BAO data, we have a much stronger upper limits, less than 0.13 EV and 95% confidence level. And that's because, okay, we are with the BAO data, we are directly sensitive to the free streaming nature of neutrinos, and we are breaking the geometrical degeneracy between the parameters. So another point we have to take into account is that when we analyze the cosmological data, we're actually using as a lower limit for the total neutrino mass 0 that is in the physical region, while we know from the laboratory that we can have the normal ordering and the inverted ordering, and so we should implement in different this different lower range when we analyze the data. If we do so, actually we have a preference for the normal ordering from the cosmological data, and when from the CMB, and when we add the BAO data, since the constraints are much stronger, and you see, but they are slightly shifted, that's because we are shifting the lower limits of the prior, we have an indication for a normal ordering of more than 1 sigma, and if combined with the non-oscillation data, this indication can reach the level 2.53 sigma. So that means that the measurement of the effective mass for the beta decay of the neutrino-less double beta decay expected okay, now by Catherine on future experiments can't really, okay, this kind of experiments can't really find anything. This is if the cosmological bounds are correct. I think we will hear more about this in the Massimiliano's talk. Okay, so another observable that we have in cosmology are the redshift space distortions, because we can analyze the clustering of in the redshift space instead of the real space. And in this case, we will have a reduction of increase of the growth structure along the radial direction because of the peculiar velocities. So if this is a map of the distribution of galaxies in the real space, this is, okay, the anisotropic clustering that we see along the radial direction in the redshift space. So with the redshift space distortion, we can measure the product F sigma 8, where F is the growth rate of the structure and sigma 8 is the clustering amplitude of the matter power spectrum. So if we have massive neutrinos, we expect less structure in the universe, that is this blue line, so we expect a lower value for S sigma 8. Okay, these values are much higher than what we expect when we have a total neutrino mass fit to vary, and that's the reason why we have this strong anti-correlation. So if we are adding the redshift space distortion data, we want a larger value for F sigma 8 and a higher value for these parameters, and this means that we are we are obtaining stronger and stronger constraints on the total neutrino mass. And so if we now consider a combination of cosmological data, Planck plus the CMB lensing, Pantheon data that are supernovae, BAO, and redshift space distortion, we see that we have an upper limits of 0.09 EV and 95% confidence level, okay, ruling out the inverted ordering at more than 2 sigma, and but we are also actually ruling out the normal ordering at about 1 sigma, because the total neutrino mass is expected to be less than 0.04 EV and 95 at 68% confidence level. And the reason is that if we allow the total neutrino mass to vary in the negative region, so okay, this is completely unphysical, so we are assuming that the neutrino mass can have a negative mass, we see that all the CMB data are picking the best fit is preferring a negative value. That means that we start to see some tension between the cosmological data and the neutrino oscillation experiments. So how can these constraints be improved in the future? Now we are here on stage 3 experiments, and the ground-based the experiment telescope, CMB telescope, at the moment the proposal with a probability of being realized. But they need large scale measurements by Planck of future experiments, because we are limited by the measurement of the optical depth that is strongly correlated with the total neutrino mass, and we can't measure these large scales from ground-based experiments. And we need a perfect a priori knowledge of the foregrounds, because we can't see all the frequencies that we can see with a satellite experiment. So Simon Observatory aims to measure the total neutrino mass with an uncertainty of 0.04 EV combined with BAO from DESI and weak lensing data from LSST. And if we replace Planck with a light wave measurement of the optical depth, we can reach also an uncertainty of 0.02 EV. Regarding CMBS4, instead, if this is combined with BAO from DESI, we expect to reach a sensitivity of 0.024 EV on the total neutrino mass. That can be improved to 0.014 EV if we have a better measurement of the optical depth. And this is very similar to the expectation we have for PICO, so a 4 sigma detection for the normal ordering, but okay, this the improvement that we can have with this kind of experiment is just with just single instrument we can measure at the same time the neutrino sector and the optical depth, and that means we don't have problem of calibrations between the different experiments. And finally, there is the futuristic CMB HD millimeter wave survey that is expected to reach uncertainty on the total neutrino mass of 0.013 eV. That means a 5 sigma detection. Okay, so everything I've said until now has been obtained assuming a lambda quadrant matter model. We will see variation of this model, how this is cosmological model dependent in the Sin's talk later. Now I want just to point out that this model is actually the mathematically simplest model that we can have in cosmology, and is based on 3 completely unknown quantities that are the dark energy, the dark matter, and the inflation. And for all the possibility, between all the possibilities for these 3 quantities, we are using the simple guesses. So the dark energy is just a cosmological constant, and the dark matter is assumed to be pressureless and cold, but we don't have any detection from direct observations in the laboratory experiment for the dark matter particles, and the inflation is assumed to be a single minimally Rorley scalar field. However, now we start to see deviations, okay, we start to see tension between the measurement of different cosmological parameters for the different cosmological probes. So this 6-parameter approach that seems more a fitting theory, so a fitting model, so it's not really a theoretical model, can start, okay, to have some cracks. These tensions that we see can indicate a failure of this model. So the tension I talking about are the Hubble constant tension out of 5 sigma between the value measured by Planck, assuming a lambda quadrant matter model, and the value obtained by the Schuss collaboration using a distance ladder, so measuring directly the Hubble constant. There are many other measurements of this parameter, and if we take just the precision measurements, we see that all of the late time Hubble constant values are higher than the early values, the values obtained by the early measurements. And this is important because we have a strong anti-correlation between the Hubble constant and the total neutrino mass. So if we want to be in agreement with the local measurement, we are going towards this direction. That means we need the stronger and stronger upper limits on the total neutrino mass. And this is the reason why if we use a prior on H0, we have a preference, a very strong preference for the normal ordering, because, okay, we are just reducing the upper bounds on the total neutrino mass. Then we have another important tension, that is S8 tension, and this is at the level 2.5 3 sigma, so not statistically significant of the previous one. But again, here we see that all the weak lengths in galaxy cluster counts, redshift space distortion are preferring a value of S8 that is lower the value obtained by the CMB experiments. And we have a correlation with the total neutrino mass as well, because if we have massive neutrinos, we have less clustering, less structure. So that's the reason why we are decreasing the value of sigma 8, and we have this correlation with S8. And then finally, we have a problem in the Planck data, that is the famous A-lens problem. Okay, lens is the amplitude of the lensing in the power spectra, and this is obtained larger than 1, 2.8 sigma. That is not a measurement directly of the lensing, that is instead equal 1. And we have this strong correlation between S8 and the lens. So we can be in agreement with the weak lensing data if a lens is different from 1. And then if we add other data sets like BAO and Pantheon, A-lens is larger than 1, more than 99% confidence level. So this is very robust. Why this is important? Because it's affecting the upper limit on the total neutrino mass. If we let this parameter free to vary, we assume that this is a systematic, we marginalize over this parameter, we are weakening the constraints of a factor 2, so we don't have any more preference for the normal ordering. Finally, we have the alternative CMB experiments like ACT and SPT. These are ground-based telescopes, and they are in tension of 2.6 sigma with Planck. This is assuming a lambda quadrant matter model, but as soon as we open to the extended models, this tension is much higher. And we see that these ground-based telescopes are preferring a total neutrino mass different from 0 at 1 sigma. And the interesting thing is that it's very similar to the value that we have from Planck if we marginalize over this possibility possible systematic in the data. And once we vary many parameters at the same time that are physically motivated, we see that we can also accommodate larger value for the total neutrino mass. And the interesting point is that the direction of the correlation is exactly opposite to what we have in a lambda Godel matter model. So now we can be in agreement with a larger value of the Hubble constant with a total neutrino mass different from 0. So this kind of model can solve the Hubble constant, also give a lower value for S8. And okay, if we look at the normal ordering versus the normal ordering for these ground-based telescopes, we see that the preference for the normal ordering disappears completely. So concluding with the cosmological data, we can easily constrain the total neutrino mass, and we have the stronger upper bounds, less than 0.09 eV, a 95% confidence level combining Planck with Biot space distortion, with the normal ordering favored at the level of 2.53 sigma if combined with oscillation and oscillation experiments. But alternative CMB data are instead preferring a massive neutrino, so with a total neutrino mass of about 0.4 EV and no indication for the normal ordering. So the fact that we have all these anomalies and tensions in the cosmological data can significantly affect the constraints on the fundamental physics quantities like the total neutrino mass, presenting a serious limitation to the precision cosmology. So until the nature of these anomalies is not clear, we should be very conservative when we consider the cosmological constraints. Thank you.
Thank you very much. That was a very interesting talk. We can open the floor now for questions from the room and from Zoom. If you're on Zoom, just raise your hand. I'd like to start us off. Yes.
This is John Ouellette from MIT. So my question is, if we assume that the lambda CDM model is not complete, that you would have to somehow extend it or modify it. Do you know for the proposed modifications, would the modifications be mostly in late time? So we would more trust the early time measurements, or would the modifications in late time affect our understanding of early time measurements? And so that we shouldn't be able to trust, maybe we wouldn't trust either.
Okay, so modifications for solving the Hubble constant tension have been proposed in the early universe and the late universe, and none of them is actually working. So at the moment, we don't have an answer. So probably it's a combination of systematics plus some new physics, or probably it's a combination of an early solution and late time solutions. Okay, but at the moment there is nothing that is really working, because, for example, if we think about the early dark energy, okay, we have more than 3 sigma from ACT, but no indication at all from Planck. And if we have a late time solution like dark energy equation of state free to vary, we are in disagreement with the sound horizon found by BAO. Okay, so at the moment is almost impossible to have a solution to all these problems.
Another question from the room.
I'm Glennis Farrar at NYU. I'd like to understand if you anticipate any resolution of this Planck ACT tension. We can't without redoing Planck, or is there an ongoing study of what systematics they might have? What's your thought?
Okay, of course, Planck is the best experiment at the moment because it's a satellite experiment. So this means that all the foregrounds are under control and that can see the large scale that cannot be seen by the ground-based telescopes. Okay, we have this problem with the lensing that we need to understand, but this has been, I don't know, checked for many years and nobody found a solution. So at the moment, there is not really, okay, so Planck won't be redone, okay. But of course, with the ground-based experiment, we can do a lot of stuff. We can have a measurement of the gravitational lensing. We can have the measurement of the small scales, and my problem, okay, my point of view is that the model that we are assuming in the lambda Godard matter model is just a model. So it's a fitting model. It was working until now because we had the very large error bars. But now that we are doing precision cosmology, we start to see some cracks in the model. So since this model is just based on dark matter, we don't know anything about dark matter. Dark energy, we don't know anything about dark energy. Inflation, we don't know anything about inflation. So maybe we have to start to change the paradigm and see what happens, okay, with the new data, trying to find a solution of this kind. But this is my personal opinion.
Just to follow up on that, as I was following your talk and what else I knew, certainly there's room for a more complex theory of dark matter and dark energy and dark matter interactions and so on, which can resolve overall tensions in the whole picture. But between ACT and Planck, that's simply an observational discrepancy, right? I mean, so I was just going to ask you if you could tell us how much of the, which aspects are purely observational stuff that has to get resolved, and as opposed to being possibly an incomplete theory.
Okay, so these are all the measurements of the Hubble constant. Let's see if you can see that. Okay, so as you can see, okay, we are always talking about these measurement being in tension with this measurement here, okay, and these are the 5 sigma. But we have many other measurements in the late time universe, okay. These are C fates, supernovae calibrated with C fates. These are supernovae calibrated with the tip of the Reggiana branch. These are the surface brightness fluctuations, and this means that are another kind of observable that is calibrated with both C fates and TRGB. Then there are masses that don't need calibration, so it's just the Hubble flow, and you can see that it's still there. You have the Tully-Fisher relationship, again calibrated with C fates and TRGB. Then we have the strong lens, and this is model dependent, but again, giving all of them an anchor value for each knot. So that's the puzzling thing, because if we assume a lambda Godard matter model, all of the measurements that are relying on a lambda Godard matter model are giving a lower value for each knot. All of the late time measurements are instead giving an higher value for each knot. So if we have a systematic something, we should expect a scatter around the true value. But this is not something we see. We see that all of the late measurements are higher values, and all of the early measurements have a lower values. So this is the interesting point of the problem. Of course, there could be systematic somewhere, but at the moment, okay, for example, this measurement has 70 different combinations, and all of them agree. With Planck, you can just change the model and you can shift these, okay, wherever you want. So it's difficult to say, okay? I think that given the number of measurement, given the high quality of the measurement, just say that is an unknown is not more enough, okay? We need something more serious because all the possibilities has been taken into account and no solution has been found.
Oh, Eleonora, I think Glenys, what he's asking is, so when you remove some of the modes, when you remove some of the L's from Planck data and you supplement that with the measurements of the CMB, you get different answers on the fit. So I think what Glenys is asking is whether there is a tension between some of the mode measurements in ACT, for instance, and Planck. Is that the case? And is that the case, or is it or that appears after you assume lambda CDM and you do all the fits? Like, can you see a tension in the measurements directly without any assumption of any model, and whether that tension can be reduced in the future, or whether it can be resolved, this data tension, if it is there? I think that's what Glenny was asking.
Okay, so yes, okay, so the point is that the measurements that are model independent are those in the late universe, okay? And here we can just improve the sensitivity, okay? So now with JWST probably we'll have better measurements, but these are model independent. These are model dependent. So if you have a lambda Godard matter model, even if you cut and if you remove some of the multiples, still you have a lower value for each knot. So you can't have H naught that is at 74, okay, 73 like we have now from the shoes measurement. Okay, if you cut, for example, there is a paper by Addison et al. If you cut the multiples into multiple regions, you have Planck, okay, multiple 1000 from 1000 to 2500, you see that the low multiple range is preferring a larger value for H naught, but it's still 70, and with error bars really large. So you are not really solving anything in that case. And this is just Planck. If you have ACT or SPT, they are still in agreement with Planck. So I don't see how you can just, okay, take a portion of the data and solve the tension. So okay, you can change the model.
Thank you.
Okay.
Do we have any more questions? All right, it looks like everyone in the room and on Zoom is satisfied. Thank you very much, Eleonora, for an excellent talk. Our next speaker is Jason Detweiler. So, all right.
Oh, that's yours. Okay.
Yes.
Okay,
All right.
and can people hear me okay on Zoom? I assume so, because they're hearing the questions in the room. Okay, I'll get
Yeah.
started.
Yeah, we are okay.
Is it just me, or can we not hear?
I can't hear.
Not
Okay.
just you.
I think that was my fault. Sean just pointed it out. Can you say something?
Yes, can you hear me now?
Yeah, we hear you. now.
Yes.
I apologize.
Okay, all I did so far was go through my outline, so you can read it. Okay, let's go on. Let me close this. Okay, so you know, in the standard model, of course, we have two particles, the neutrino and the antineutrino. So, for example, the sun emits neutrinos that are left-handed particles, and reactors emit antineutrinos that are right-handed particles. All the neutrinos we observed to date are ultra-relativistic, and we only needed two components until you know the turn of the century, when neutrino oscillation was discovered, and we realized that it would be possible to boost into a frame in which the neutrino is at rest. And in that frame, we have two options. So one option, Dirac neutrinos, where there's two new sterile components. And so, you know, the neutrinos that we see are this sort of half sterile object that if you boost in the direction opposite to its spin, you get the standard model neutrino. And if you boost it in the other direction, you get a sterile right-handed neutrino. The other option is that the neutrino is truly Italian, Majorana particle, and when it's at rest, it has both particle and antiparticle-like behavior. So the best known way to probe this possible nature of the neutrino is to search for neutrinoless double beta decay. Because if the neutrino is a Majorana particle, then you know, it could be, you can think of it as being emitted in one decay vertex as a neutrino, and having a chirality flip that allows it to be absorbed as an antineutrino, or you can view it as you know, two neutrinos annihilating each other before they ever leave the vicinity of the nucleus. And in that case, you could have this process where two electrons are created and no neutrinos. And if you measure the summed energy of those two electrons, you get a tiny little delta peak at the Q of the decay, allowing you to distinguish it from the standard model process, in which two neutrinos are emitted, carrying away much of the energy and giving you this broad spectrum here. And yeah, so I've drawn this with a branching ratio of 10 to the -4, which is more than an order of magnitude above the current experimental limits. So this peak is truly very tiny. And experiments are continuing to place a stronger and stronger limits on this. And the connection between neutrinos double beta decay and the neutrino mass scale is the height of this peak, because you can look at this Feynman diagram and you see UEI, M sub I, UEI. So there's a term that is proportional to that in the amplitude, and you sum all the possible diagrams and square the amplitude, and that'll give you the contribution to the decay rate. So this combination, which by the way is also the the Majorana mass of the electron neutrino, is what probes the neutrino mass scale in this context. And so if we here's this classical lobster claw plot that plots the possible values for M beta beta, which is this combination here, versus the lightest neutrino, which is M1 in the case of normal hierarchy, or M3 in the case of the inverted hierarchy. And and so we get these two regions where we predict possible solutions. And in the case of inverted ordering, we get sort of this hard lower limit on M beta beta, and that implies that we should be able to detect neutrinoless double beta decay with half-lives on the order of 10 to the 28 years or lower if the standard model neutrino is a Majorana particle with inverted ordered masses. In the case of the normal ordering, there's a possible cancellation here due to the Majorana phases inside of the PMNS, the mixing matrix. So it's possible for M beta beta and hence the decay rate to go to 0, although that's very unlikely, as I'll show you later. And so for the bulk of the parameter space, there's sort of a lower limit here that implies an upper limit on the half-life of about 10 to the 30 years. So these are very clear experimental goals, and that coupled with the observation of neutrino mass that really brought this question of the nature of the neutrino to the forefront has really pushed the global interest in this process. However, the light neutrino exchange is not really the only thing that can happen. There's many other possible mechanisms. In general, you have some lepton number violating process, and you end up at the end of the day with two new leptons, no new anti-leptons or anti-baryons, and so regardless of the connection to neutrino mass, neutrinoless double beta decay is being pursued with great interest. In particular, this is I like to call it a little bang as opposed to the big bang, where you're creating two new matter particles, and I think it's also important that this violates not just lepton number, but also B minus L, which is the last accidentally conserved quantity in the standard model. Now with these many other mechanisms, now there's the Schechter-Vallée theorem or argument that all of these will induce some sort of neutrino mass, but actually the Majorana mass terms or contributions that they introduce are many orders of magnitude smaller than the solar mass splitting, for example. So it might be that they that the Majorana that it might be that double beta decay occurs, but neutrinos are dominantly Dirac particles and don't actually participate strongly in the process. And even in the case of light and neutrino exchange, there's something that kind of separates double beta decay from the neutrino masses, which is that whatever physics generates the Majorana mass of the neutrino, as Vincenzo and company pointed out, will also give a short-range leading contribution, a contact term that contributes at leading order to the decay rate. Now that it often gets parameterized like this, so that these matrix elements can be compared to each other, but this term that has this short leading order term, it basically has a factor of M beta beta pulled out of it. So it really is just kind of like an additive piece here to the process. Okay, so some truth in advertising, since I've been asked to talk about how well double beta decay probes the mass scale. So if neutrinoless double beta decay is observed, it might be that it's not mediated by standard model neutrinos at all, in which case there's no connection. Even if it is mediated by standard model neutrinos, so there's still large uncertainties that I don't have time to talk about in the nuclear matrix elements, and the questions of quenching is part of that, and also the contact term that I just mentioned. Even if we could recalculate those reliably, it could be that M beta beta is in a region where its value is not very well correlated with neutrino masses in one of these broad bands. Oh, I didn't finish that sentence. The unknown Majorana phases in the mixing matrix elements generate an additional degeneracy that keeps us from being able to connect the two. In the case that neutrinoless double beta decay is not observed, it could be because of large cancellations, or it could be due to cancellations in M beta beta itself from the Majorana phases. So this like funnel that goes down to zero in the normal ordering, or it could just be that neutrinos are Dirac and we just can't see neutrinoless double beta decay. So, neutrinoless double beta experiments, truthfully speaking, do not really directly or reliably probe the neutrino mass scale. That being said, if we write the Lagrangian for nature in terms of the standard model plus increasing higher order terms, as Vincenzo and company pointed out, lepton number violation appears in terms of dimension 5, 7, and 9, and etc. The dimension equals 5 operator is uniquely a Majorana mass term for the standard model neutrino. This appears sort of generically out of many scenarios, and a really good example that's highly well motivated is the SO10 grand unification theory. So SO10 unifies the leptons and the quarks, but requires one new particle, a right-handed singlet, which we call capital N. That heavy singlet can generate, it acts as a new mechanism for generating the masses of the neutrinos, and does so via, for example, the seesaw mechanism here, the type 1 seesaw. And that same particle would be produced early in the universe. And if you have CP violation, then the decay to matter can occur more rapidly than to decay over antimatter, giving us leptogenesis. And that's sufficient as maybe one of the leading theories to describe the cosmic matter asymmetry. So this has led to what my co-author Bassani calls a sort of an orthodoxy. For a large class of models, it's pretty natural for light left-handed neutrino exchange to be the dominant process in neutrinoless double beta decay. I think you can also think about it in terms of like, what new parameters are we going to add to the standard, the new standard model of nature. Light left-handed neutrino requires only a single parameter, which is that Majorana mass term of the standard model neutrino, and doesn't have to rely on any new specific field or symmetry. As I mentioned before, this sort of standard picture gives us these very clear experimental goals. And for sure, if discovery is seen, the first thing experimentalists will do is interpret it in terms of M beta beta, and then interpretations into other possible mechanisms would proceed after that. And I think that would continue until there's some evidence of tension in that model. So within this orthodoxy or this model dependence, both the observation and the non-observation of neutrinoless double beta decay is connected pretty directly to the neutrino mass scale. And so the rest of the talk will assume that. Okay, let me go on to the global experimental program. What am I doing? Okay. So yeah, there is a very large number of experiments racing to try to be the first to detect this process. There we have bolometers, external trackers, scintillators, semiconductor detectors, TPCs. This is just a picture of a small fraction of them. And in order to discover neutrinoless double beta decay, the really critical experimental observable is that energy. It's necessary, it's required in order to distinguish the standard model 2 neutrino double beta decay from neutrinoless double beta decay. And it's also sufficient if that was the one thing you measured and you had zero background and you saw just one, one or a few counts right at the right energy, you would have your ticket to Stockholm ready to go. So yeah, it's the one necessary and sufficient observable, and that means that the that to first order, the sensitivity of these experiments is dominated by the Poisson fluctuations in how many counts you get from neutrinoless double beta decay right near that energy relative to background processes, including 2 neutrino double beta decay. There's 2 relevant parameters then. One is the sensitive exposure, which is the combination of the efficiency, the total detection efficiency, the mass of the isotope in the fiducial volume of the experiment, and the counting time. And then the sensitive background, which is the total number of background events you would count during that time, divided by the sensitive exposure. And the statistic that we use to sort of compare experiments or talk about their capabilities is the discovery sensitivity, which is the value of T1/2, the value of the half-life for which an experiment would have a 50% chance of making a 3 sigma discovery or greater. If you look at how that varies with the sensitive exposure, if you have a background-free experiment, it just increases linearly, and it very rapidly degrades as you start adding just a couple of counts of background. So here's a listing of sort of recent or in progress or proposed experiments. And you can see we have many isotopes, including germanium, xenon, tellurium, molybdenum, and selenium. The colors here go with the what's it called? The isotope. And in general, semiconductors are used up here for germanium. Xenon is used in liquid and gas TPCs as well as liquid scintillators. Tellurium you can also find in liquid scintillators as well as bolometers. And then in the bolometer community, there's a move towards molybdenum. And then for selenium-82, there's trackers. There's also selenium bolometers, but not here. So, what I wanted to say is you can kind of see that the gas TPCs, the liquid detectors, the large volumetric detectors are good at getting to very high masses, giving them very high sensitive exposures, contributions to their sensitive exposures. On the total efficiency, you can see that the semiconductors and the bolometers sort of win out a bit because these detectors that achieve high masses also require high fiducialization. So it kind of knocks things down a bit. The energy resolution, which impacts very strongly how that sensitive background, how much background you have to accept near your ROI. You can see that semiconductors and bolometers have the highest resolution, with the TPCs sort of coming in second, and then liquid scintillator detectors, which can reach really giant masses, but have a challenge to measure energy precisely. And you put those together, and you can see that there's a few detectors that reach the highest sensitive exposures. Here, Legend and EXO Snow Plus. And then a number of detectors that we reach the lowest sensitive backgrounds. Again, Legend, Nexo, a few other detectors here, and you can see Cupid comes in down here. We can put them all on one plot where bands across here are half-life limits. And you can see that there's a march, this is the good region to be in. There's a march in sensitivity down here, and it might look like Legend is doing the best, but you have to remember that there's the nuclear matrix elements and phase space factors that you have to take into account. So you can kind of see that, here's for the QRPA nuclear matrix elements, here is 18.4 millielectron volts. That's the lower limit of the inverted ordering. And Legend is sort of about this far ahead of that. And you can see for Xenon, Nexo is about just about as far as that. And then here's Cupid. It looks like it's way back there, but it's sort of also well ahead of its 18.4 line. And so you can sort of flatten that out and put them all on a line here. And you see for the various different matrix elements, you see some clear leaders in the field with Legend, Nexo, and Cupid, with also Amore and Next and others reaching this sort of lower edge of the inverted ordering. And so this just kind of really zooms in on that 18.4 milli eV lower edge of the inverted ordering. And so for 3 isotopes, we have these experiments poised to reach, really fully cover the inverted ordering for most nuclear matrix element calculations, and doing so with different techniques. And for some of, I'd say many of the nuclear matrix elements, these experiments are reaching far beyond the normal inverted ordering, like well into the normal ordered region. And a lot of these experiments are being designed with upgrade capability to push further into the normal ordering. Okay, let me finish up by talking about what that experimental program will get us, we hope, in terms of inference of neutrino mass. So here's where we are right now. These are sort of recent limits. Just a couple months ago, CamLines N800 came out with the new most sensitive limit that digs for the first time deep into the inverted ordering for the strongest nuclear matrix elements. Of course, where this limit is dependent on which nuclear matrix element you choose. So there's sort of like a factor of 3 to 4 variation here, and that same thing is happening here for what would be the updated version. And of course, our next generation goal is here. That would cover the IO. It probes this significant portion of the normal ordering here, and also is just a nice aggressive experimental goal. You can think about it in terms of like trying to assign some volume to the phase space in a Bayesian sense, and looking at what fraction of that phase space will be covered by the next generation experiments. And if you say, well, this M-min, the minimum mass could be anything, any order of magnitude. Then in any slice, you can see that there's like a higher phase space, like sort of towards the top of each of these regions. And the inverted hierarchy also has a high density region sort of down here. But you can see that at the ton scale, we're sort of covering all of the inverted ordering. And in the normal ordering, there's some space here, but if the natural cutoff for this M-min is 10 to the minus 13 EV from loop correction. So there's just a lot of phase volume way down here. So if this is your picture, which you would, this might be your picture if you think that the neutrinos are normal ordered, and then they're like all the other leptons, and then those masses just get suppressed by some mechanism. Then you might say that the ton scale experiments will probe very little of the normal hierarchy. On the other hand, you could, in other models, you could think of like the neutrino masses start at some scale and then get split about that scale, in which case your prior might be on, for example, sigma, the sum of the neutrino masses. And because sigma has a minimum due to the oscillation experiments, there's sort of a very vanishing space for the lightest neutrino mass in the normal ordering to become vanishingly small. This sort of cuts things off down here. And in that sort of a scenario, very broad case of scenarios, you would have a discovery probability of on the order of 50%. See, roughly 50% of the shaded region is cut here. So yeah, so it's sort of like up to you to decide what you think the discovery probability is in a Bayesian sense. But I think we can look at what would happen in the case of a possible discovery scenarios. And there's three scenarios that you can break it down into. So it could be that neutrinoless double beta decay is just beyond the reach of the current experiments. And in that case, we would expect the next generation experiments to see hundreds of counts. So the statistical uncertainty would be on the order of 10%. So if, like we measured at this blue line, you would have some sort of uncertainty on the order of very small uncertainty like this shaded blue region. And you would propose to do follow-up experiments, which could see hundreds or thousands of counts, but also with the ability to look at the opening angle between the betas so you can probe the Lorentz structure of the mediating mechanism. Could be though that the half-life is on the order of 10 to the 28 years and near the bottom of this inverted ordering, in which case we'd have a few counts to 10 counts. The next generation experiments would just be sort of discovery experiments. The statistical uncertainty in that case would be on the same order as the uncertainty, well, not the uncertainty, but the variation in the nuclear matrix elements. And you would want to follow up with more ton scale or greater experiments, probably 10-ton scale sort of experiments, to confirm the discovery and maybe try to develop the technology to maybe probe the decay mechanism. The other option is that it's just too long to see in the next generation. We would see less than a few counts, and you would want to look at R&D. Why did I not finish that? You want to look at R&D, the R&D required to push down lower, to lower costs in particular, to find the technology that could reach deeper into this normal ordering. Okay, so there's some interplay though with measurements of the neutrino ordering. It might be that, well, we expect the neutrino ordering to be measured by Juno and by Dune and other experiments. So interestingly, if the ton scale experiments observe neutrinoless double beta decay, in the inverted ordering, they're almost guaranteed to observe neutrinoless double beta decay, but the inference that we would make on the neutrino mass scale is pretty weak because this is a very broad degenerate region. You can only, if you measured it here, you would only say that, the neutrino, the lightest neutrino mass is less than on the order of 100 milli electron volts. In the case of the normal ordering, though, you would get some sort of range here. And if you had an experiment like Project 8 coming in and giving you a vertical line here, actually, the value of the what's it called, the neutrinoless double beta decay experiments, you'd get some information on the unknown or the relative phase between two of the Majorana phases. In the case of the neutrinoless double beta decay is not observed, if neutrinos are shown to be inverted ordered, you might conclude that neutrinos are Dirac, or at least mostly Dirac, to within the model dependence that I discussed earlier. In the case of the normal ordering, if you don't observe it, then you would conclude either that neutrinos are Dirac or that the mass has to be less than roughly the m beta beta that you measure. There's a nice, in 1 more minute, I'm almost done. So there's a nice interplay between m beta beta and m beta. This is how those, there's a large overlap between the inverted and normal ordering there, and the space breaks up like this. So if we measure, say, m beta beta here, that gives you a prediction for m beta, sort of on the same scale as m beta beta, but it has a large uncertainty because of those Majorana phases. And the Project 8 specs would maybe be somewhat loosened if we saw it in the ton scale, because it would mean that you don't have to go all the way down to the bottom of the normal hierarchy, down to this region. And on the other hand, if Catron measures m beta, measures a positive m beta, then we have a really good chance to measure the Majorana phases. But we would also probably want to look at issues with the nuclear matrix elements. Maybe there's something like quenching that opens up this region. And we think we're probing here, but really we've been probing here, that sort of thing. If neutrinoless double beta decay is not observed, then we would say that neutrino masses must be sort of in this kind of range here. And if neutrinoless double beta decay is not observed and Catron observes m beta beta, we would conclude that neutrinos are dominantly Dirac, or there's some big cancellation going on. Finally, I'll mention, sorry, in 1 second, sigma. So if neutrinoless double beta decay is observed, it would mean that the neutrinos are, it would imply a large value for sigma, and we would sort of go back to the looking at some of these alternative scenarios that were discussed just by the previous speaker. And you would probably use sigma on the order of 3m beta beta as an input to the lambda CDM fits. And if it's not observed, you can get some constraint. Sorry, that was poorly worded thing. Okay. If it's not observed, it doesn't have much impact on cosmology. Okay, I think I'll finish there. So we have a very aggressive international program to search for neutrino double beta decay. It's poised to really probe the inverted ordering, which at the same time really digs deeply into the normal ordered region as well. And although neutrino double decay is connected to neutrino masses only in a model dependent way, it does so for a very broad range of models and is a pretty good sort of orthodoxy. So yeah, so we do expect that both the discovery or limit on neutrino double beta decay will provide some important information on the nature of the neutrinos, the masses of the neutrinos, perhaps even the Majorana phases in the mixing matrix. And I'll stop there. Thanks.
Thank you very much. I think we can make time for one quick question if someone in the room or Zoom has. If you're on Zoom, please raise your hand. I had a question, but it's not quick, so I might save it for the further discussion later.
I have
Yes.
a possibly out of scope one, so apologies for irrelevance, but so you showed on your sensitivity plot, you actually had like LZ and Darwin on there, and they didn't look too bad. So why do we need dark matter detectors and something like an EXO at this? Like, what fundamentally stops them from being the same detector?
What fundamentally stops them from being the same detector is that the instrumentation that's needed to sense those extremely faint recoils in the case of Darwin and LZ gives you A, lots of background, and B, some sort of dynamic range kind of issues. I think the dynamic range is pretty easy to handle, but the background is one that's difficult. And another one is just scale. So like Darwin is a huge experiment, and if you wanted to put enriched isotope in it, it would blow up its cost by orders of magnitude sort of thing. And so those experiments have to run with natural xenon at least in the initial phase. And even if you propose to upgrade them, you have to deal with trying to procure that much xenon to begin with. So it's a sort of a long time scale sort of thing. And so, they have good sensitivity, but they're orders of magnitude behind Nexo, which is a much smaller experiment. Yeah, it's just really hard to design experiments that do both.
Thank you.
Okay. Thanks. I think we'll close out this talk for now. Thank you very much again. Our next and last speaker before the break is Massimiliano Lattanzi. Dr. Lattanzi is going to tell us about discovery scenarios between the three probes. Could you please share your screen?
Yeah, thanks, Diana, for the introduction. And yeah, but I mean, for everybody, you can just call me Max. I know it's easier, it's certainly easier for non-Italian speakers. So let me share my screen and also give you the video for a moment, but because I'm on a slow connection. So the screen first. Okay.
The screen looks good.
Can you see it?
Yes.
Okay, so that's me. I don't know if you can see me. So yes. I'll try to start with the video turned on, and then if I see that the connection is too slow, then I will switch it off. Okay, so without any further ado, so yeah, let me introduce this talk. So in which I've been asked to talk about, let's say, prospects for joint discovery scenarios among the three probes, which are the ones that we have just heard about. So kinematic measurements, neutrinoless double beta decay searches, and cosmological observations. So of course I should say it's three probes plus one, because everything here assumes that the measurements from oscillation, from flavor oscillation experiments, apologies. And the other thing that I wanted to say is that this is based on the discussion that is in the white paper that we have coordinated with Martina Gerbino and Evan Gross on the synergy between cosmological and laboratory searches. So the discussion there was quite qualitative, was meant as again, as an idea of what we can do by combining the three probes together. So the talk basically will follow that. So there is not this is a disclaimer, there is not a proper statistical analysis here, which is definitely something that would be worth doing at some point, but these are more qualitative considerations, which again are based also on what we have just heard from the other speakers. Okay, so let me start. So again, let me recall you, we have these three different probes of the absolute mass scale, and they are sensitive to three different combinations of the mass eigenvalues and of the elements of the mixing matrix. So since we measure very well both the angles and the mass differences through oscillation experiments, you can think that basically these quantities here, with one exception, which I will tell you in a second, these quantities here are basically depend only on the mass of the lattice eigenstate. Again, given some assumptions that to which I will come back in a second, that we have also partially heard, or not partially, that we have heard already. So the exception, of course, here is the neutrino-less double beta decays and beta beta that also depends on the Majorana phases, as we have heard now by Jason. And so this kind of widens basically the relationship between the mass of the lattice eigenstate and the effective Majorana mass of the electron neutrino. But we can think of the Majorana phases as nuisance parameters on which we might want to integrate over when we do a proper statistical analysis. So the point of view here would be mostly that these quantities that you see here are functions just of the mass of the lattice eigenstate, and of course of the hierarchy, of the ordering, okay? We also know that given, again, for a given ordering, we have minimum values for all these parameters. The only case in which one of these mass parameters can vanish is the Majorana mass of the electron neutrino in the case of normal ordering. But apart from that case, we also have non-zero minimum values. The other thing, of course, to be taken into account, as it has been said, is that, of course, we are not really, I use the expression that experiments are sensitive to these parameters, but they didn't say that we are measuring directly those parameters. So again, here the exception is beta decay. In that case, we have a direct measurement, the measurement of M beta. But in the case of neutrino-less double beta decay and cosmology, the quantities that we are measuring, which are the lifetime for the neutrino-less double beta decay, or for example, the CMB power spectrum for cosmology, they depend on the quantities that are written here in a model-dependent way. Okay, so this should be borne in mind. I think we will hear more about this in the following talks. Also, we had an insight of this from Jason about neutrino-less double beta decay, from Eleonora for cosmology. So yeah, again, this is something that should be kept in mind. So let's say that what I will do in this talk, I will basically take 2 points of view. So one is that I will assume that the standard, let's say, theoretical framework, okay, in which we interpret neutrino-less double beta decay and cosmology, so respectively the mechanism for mass generation, so the fact that neutrino-less double beta decay gets contribution mainly or exclusively from the mass generation mechanism. And on the other side, for cosmology, I will assume that the lambda CDM model is correct. So I will start with that assumption, say what we can expect to measure given this assumption. And then in the last part of the talk, I will briefly touch on what we might hope to learn, okay, if instead this is not true and the data and the observations hint in that direction. So we have some tensions among observables. Okay, so the game here is basically we have, again, 3 observables, which to some approximation depend on only one parameter, which is M0, which is M0 is the mass of the lightest eigenstate. So we can plot the allowed regions in the plane for each pair of observables, okay, in the case of neutrino, of normal and inverted ordering. So this is the plot for the sum of the masses and beta beta. So again, the blue is for normal ordering, the orange is for inverted ordering, and I'm also showing the constraints that we have from the current constraints that we have on these observables, and taking Kaplan's N for m beta beta, which is, as we have heard, the strongest one. For cosmology, I'm taking the Planck plus BAO, again, derived in the framework of lambda CDM cosmology. Of course, this might change if we include other data. We have heard that including other data pushes the bound even below the 100 MeV, which is the benchmark for inverted ordering. But for this discussion, I will be conservative and just consider this Planck plus BAO limit. Again, this is the same plot for m beta beta versus m beta. Of course, you don't see the current constraints on m beta here because they are out of scale. They're outside the edge of the plot. And again, this is the same plot for some of the masses versus the effective mass of the electron neutrino. Now, so there are basically, I mean, if we stay in this framework of what I call concordance, in the sense that we get coherent, okay, results from all measurements, from all kind of probes, there are basically 2 possibilities. Before I go on, just let me tell you what I'm assuming here for the sensitivities, okay, of future experiments. So for the neutrinoless double beta decay, I'm assuming that that next generation experiments will be able to probe all the region, okay, that is covered by both the normal and inverted ordering. So this means I'm assuming that everything above 18 MeV can be measured can be detected at 3 sigma level. Okay, for cosmology, I'm assuming a sensitivity of 20 MeV. So I'm assuming that the sum of the masses can be detected again at 3 sigma level, that everything above 60 MeV, which is the benchmark for the normal ordering, can be detected at least 3 sigma level. As we have heard from Eleonora, this is a number that we might reach in the relatively near future by combining data from Simon's observatory with a measurement of the optical depth to reionization from a satellite like LightBird. While for the beta decay, so for kinematic measurements, I'm assuming the target sensitivity of Project 8, which is 40 MeV at 90%, which more or less translates to a 3 sigma level, 3 Gaussian sigmas of 50 millielectron volts, give or take a few millielectron volts. This is, of course, as we have heard, is a bit farther in time, okay, with respect to cosmology and neutrinoless double beta decay next generation experiments. So I will start by talking only about the combination of neutrinoless double beta decay searches and cosmology, and then see what the kinematic measurements can add. Okay, so the first situation is the one in which we get, again, we have a measurement, okay, of both, we see neutrinoless double beta decay, and we also have a detection of non-zero mass from cosmology. So this means that we are in this sorry, can you see my, okay, here it is. So this means that we are in this region here. So what can we say in this case? Let me add this, sorry, just one thing that I forgot to say. Of course, here we are seeing coherent observations, which basically means that we lie within the contours here. But of course, this does not imply that the theoretical frameworks are right. I mean, this only implies, I mean, if we see something outside, then probably the theoretical frameworks are wrong. But if we see something inside, there is no guarantee that the theoretical frameworks are good. But as also Jason was saying, let's take again the point of view that if we have no reason to think differently, so if we have no tension, we assume that our theoretical frameworks for neutrinoless double beta decay and cosmology are correct. Okay, so again, we see something in this region. So I have an example here, the red dot. So of course we are measuring the mass scale. We are seeing we see neutrinoless double beta decay. So neutrinos are Majorana. We don't know about the ordering because this is a region in which the ordering, as we know, can be either normal or inverted. Now, how can we measure? And we can't measure the ordering from cosmology as well, in the sense that here cosmology has a simple way of determining the ordering, which is measuring a mass which excludes 100 MeV, okay, which is below 100 MeV at a statistically significant level. Okay, now in this case, as you see, the mass has to be of the order of 100 MeV or maybe larger, even though that's basically a small window with respect to the currently available constraints. But in any case, we cannot determine the ordering from cosmology. We can determine it from oscillations, for sure, as we have heard. But staying to probes of the absolute neutrino mass, a hint might come from a project 8 sensitivity. I mean, because if we have that in this region, basically you have that the mass of the m beta has to be at least 50 MeV for inverted ordering. So this means that we might expect a mild 2 sigma detection, okay, of m beta if the ordering is inverted, okay. Sorry, I think earlier I said that 50 MeV is the equivalent of 3 Gaussian sigmas. No, sorry, it's the equivalent of 2 Gaussian sigmas. It's more or less the 95% confidence interval. So of course the sensitivity is even if you take this 40 MeV sensitivity, it's probably not that much to distinguish if you look at this figure here, to distinguish these two curves, okay, at a high statistical significance, but might still, let's say, give a hint, okay. So again, in this scenario, project 8 with this target sensitivity might give a hint towards the ordering that basically cannot be determined in this way. Now, the other scenario is that we observe a non-zero mass from cosmology, but there is no signal in neutrinoless double beta decay, and then this means that we are in this region here, if neutrinos are Majorana particle, of course. Okay, so again, we get a measurement of the mass, and there are two possibilities why you don't observe neutrinoless double beta decay. So one is that neutrinos are Dirac, okay? So basically, we don't know, we have no way, sorry, it's not that we have no way. I mean, we cannot say in principle what the ordering is, but again, we might get it from cosmology, okay? Because if the cosmological measurement is, let's say, in this side here of the figure, then we know that the ordering is normal. Or again, we might get a hint from m beta. For what concerns m beta, we don't have, let's say, a guaranteed detection, in the sense we don't know. Again, since we don't know the hierarchy, the ordering, basically, we cannot tell whether we could expect a mild detection of m beta from project 8. Of course, there is another possibility, which is that neutrinos are indeed Majorana, but you have that the ordering is normal and the phases arranged in such a way to make the signal disappear. In that case, we do not expect a statistically significant m beta signal. So detection, I mean, a measurement of m beta, again, might give us a hint towards which one of these two scenarios is the right one, in the sense that if we measure m beta, okay, then we have to be in this first scenario here and not in the second one. Okay. Now I'm trying to summarize all this in this table. So note that in my concordant scenarios, sorry, I'm always assuming that that we have a measurement from cosmology, and this is because again, if we in the theoretical framework that I'm in, the mass is at least 60 MeV, and cosmology should be able to measure that, given the sensitivity of future experiments. So this is a table that again kind of tries to summarize this. So this is whether you are measuring each one of these quantities. This is whether you are Majorana or Dirac. This is the preferred hierarchy. And these are some notes that basically amount to say that in all the cases, in all these cases here, the sum of the masses should be at least 100 MeV, so kind of a bit in tension with current cosmological data. So again, if you measure both the sum of the masses and then beta, of course, you are Majorana, and you cannot tell the sum is anyway to be larger than 100 MeV, or in that, let's say, in that ballpark. So you don't have a way to tell the ordering from cosmology, but measuring or not measuring m beta might give you a hint towards which one is the preferred ordering. Now, if you instead measure some m nu, but you don't measure m beta, then you might be in one of these two cases. So either neutrinos are Dirac and ordering is inverted and the mass is, so to say, large. But in that case, you should see m beta. So if you see m beta, sorry, if you see m beta, you can say that you are in this scenario here. If you don't measure m beta either, then really you don't know nor the Majorana or Dirac nature, and the mass can be, let's say, everything within the currently allowed limits. But then you are sure that the ordering is normal, because if it were inverted, you should observe m beta. Again, in all these cases in which the ordering is inferred from m beta, this is a hint. In this case, you might have a firm measurement of the ordering also through the measurement of the sum of neutrino mass from cosmology. And then, of course, always keep in mind that the ordering can be determined by oscillations. Of course, we can also have non-coherent results, which add up discordance, which are as interesting as, and probably they are more interesting than concordant scenarios. Now, these are, again, more difficult to discuss, let's say, without having a model in mind. No? So I just make some considerations. So one is that if we don't see a non-zero neutrino mass from cosmology, this is a failure of the standard lambda CDM model, regardless of what we see or we don't see in laboratory probes. Okay, still laboratory probes, other than being able to pinpoint the absolute mass scale, will be very useful also from the cosmological point of view, because they can constrain the mass scale and the ordering by themselves. And then when we, as cosmologists, so this is a very cosmologically skewed point of view, but let me say then, if we look for an alternative model that tries to explain why neutrino masses, why we don't see neutrino masses in cosmology, having information on the absolute mass scale will allow us to assess the variability of models that try to explain this fact. Another thing that should be kept in mind is that many proposed modifications to the standard cosmological model that allow to get larger neutrino masses involve non-standard neutrino properties. So some of the solutions are just modifying the properties of dark energy, so nothing in principle related to neutrinos. But there are many models in which people modify neutrino properties. Then one thing that one might ask is whether we can probe those non-standard neutrino properties in the lab, for example, by looking at coherent elastic neutrino nucleus scattering. Okay, so I will skip this slide, but this is a compilation of models in which you have non-standard neutrino properties and you can relax the neutrino mass bound. In some cases also you can relax it as much as to reopen the window of rad detection in covering, which is very interesting, I think. There is another class of scenarios, of discordant scenarios, in which you get measurements of both cosmological or neutrino masses from cosmology and neutrino double beta decay, but they are discordant, so they lie outside the contours in the previous plots. So given the current sensitivities, unless you relax a lot the current limits, the scenario that you expect, the most probable, let's loosely say this, is that you get a too large M beta beta. So for your given some new plus oscillation measurements, the M beta that you observe is larger than the one that you expect. So this will point to the need for revision in both theoretical frameworks. So it might be that M beta beta is larger because it's getting some additional contribution other than the mass mechanism, or that your sum of the masses is actually being, let's say, hidden in cosmology. So the value that you measure in cosmology is actually a biased estimate towards low values of the sum of the masses. So again, kinematic measurements will be crucial in, again, telling us, for example, whether the problem is in neutrino double beta decay or in the sum in cosmology. And also take into account that cosmology itself might be also informative, because if we think, for example, that we have a light sterile neutrino contributing to the amplitude for neutrino double beta decay, we might try to see whether this sterile neutrino gets populated in the early universe, and in that case it will contribute to an effective, plus biasing as well your estimate of some mu, because when you're looking at the sum of the masses, you will be basically measuring also the mass of these additional sterile ligand states. So these are just some possibilities, but I hope that I have given you an idea of the landscape of possibilities. I don't have a final slide, I don't have a summary. Let me just say that I hope that we all agree on this. Probably there is no need to say this, but I mean, this comes from a cosmologist, but I mean, we really need everything. We really need all kinds of information. We don't just have to look at the sensitivities. We really need information from all probes to really pinpoint neutrino masses and maybe discover some exciting new physics. And in particular, I'm really looking forward to Project 8 at its final nominal sensitivity. Thank you so much.
Thank you very much. Is there maybe one quick question from the room or from Zoom? Jason.
Max, thank you very much. On your table of concordance scenarios, you had a line where cosmology makes a discovery, neutrino double beta decay makes a discovery, and M beta doesn't. You suggested in the notes that the sum of the masses would have to be greater than 100 milli UV, but isn't there a lot of flexibility down towards the bottom of the inverted ordering where you could see neutrino double beta decay, and you know, basically all bets are off for the sum of the neutrino masses? It could go all the way down to 60 milli UV.
Okay, the point here is just that if you see something with M beta beta with this sensitivity, so this basically assumes that M beta beta is larger than 18 MeV, and then if you look at this plot, you have that basically the sum of the masses must be larger than 100 MeV, but this is a statement related to the sensitivity, okay, of neutrino double beta decay experiments. If you can go below that number, okay, then yes, this implication is not true anymore.
I guess my point is that, you know, the uncertainties in M beta beta and the next scale will be, you know, factors of 2 in statistics and factors of 2 in the or more in the nuclear matrix elements. And so if you go back to that plot,
okay,
you know, you put some error bars on there and you can accommodate sort of all the way down.
Okay, no, okay, yeah, I see your point. That's probably true. That's why, probably a more detailed statistical analysis would be should be true. So I don't know if that really can get you down to 60 MeV, but that probably, no, you're right. I got your point, and yes, correct. I mean, you probably got part of the normal, sorry, of the region below 100 MeV.
Okay, thank you very much. So that tranche of 4 amazing talks was the first part of the session. We're running a little bit behind, but I'd like to preserve the break. So we'll start again at 10 minutes after the hour. And then we'll delve more into model dependence and what that means. So thank you very much, everyone, so far.
There's a Starbucks in the basement.
So, hi, welcome back, everyone. I hope you had a restful break. Steen, could you go ahead and share your slides?
Absolutely. Hang on. Do you see my screen now?
Yes, we do.
Very good. Okay, so hang on, let me just switch to pointer.
Okay, looks good. We hear you, we see you, we see your
Okay.
slides.
Excellent. Very good. Okay, morning everyone. I'm also going to talk about neutrinos in cosmology. And of course, we already had a very nice talk by Eleonora about neutrino mass bound from cosmology and presenting all the various observables and so on. And you also heard from Massimiliano at least some things about potential model dependence in neutrino mass bounds. And in fact, my talk will be mostly about modeling of neutrinos, as you'll see. So it's a little bit complementary to what Eleonora talked about. Now, going back to basics, of course, this you've seen before already this morning. Neutrinos are, well, a source of dark matter and entirely within the standard model, just weak interactions plus GR. We know that neutrinos decouple around a temperature of 1 MeV in the early universe, and slightly after neutrino decoupling, you have E plus E minus transfer of entropy to the photons, which means that you heat the photon distribution relative to the neutrino distribution by this factor, which is accurate to about 1% roughly. Now, if we go to the current universe, that means that we can actually make a direct translation between the sum of neutrino masses, so counting basically all the non-relativistic mass states, and the neutrino energy density at the moment via this relation that you also saw before. Now, of course, neutrinos are very different from cold dark matter in the sense that they are very light particles, which means that they go non-relativistic very late. And that means they have extremely large free streaming lengths. And if you take just a 1 electron volt neutrino, that would have a co-moving free streaming of gigaparsec scales, basically. So that would mean that you essentially erase all structure below this free streaming scale. And you can see just an illustration of this. So this is an old plot showing two different in-body simulations, one with a standard lambda CDM model and the other one with massive neutrinos replacing some of the cold dark matter. And I think it very nicely illustrates the point that if you have significant contribution of energy density from neutrinos, you have very little structure on smaller scales. On large scales, you have essentially the same structure. You can't tell the difference between massive neutrinos and other types of matter. Now, if we briefly go through, you've seen this before, so I'll go quite quickly through it. If we see the cosmological data that we have available, then it's primarily, of course, the CMB. And, oops, sorry, in the form of the power spectrum, it looks like this. It's, of course, always impressive to see. Now, neutrinos at first sight wouldn't have much, or at least neutrino mass wouldn't have much effect on the primary CMB spectrum because it's formed at a temperature of about 0.3 electron volts in the early universe. And if you have a neutrino mass in the same ballpark, maybe even a little bit smaller, neutrinos are completely relativistic at the time of recombination. But as Eleonora also pointed out, you do have a very substantial effect from neutrino mass, but that comes in later through weak lensing. So all of the effects of weak lensing on the CMB spectrum is changed dramatically if you have massive neutrinos. And that actually does make the CMB quite sensitive to neutrino masses. Now, of course, we also, as you also heard, have more direct ways of measuring structure at lower redshifts, which are more, at least at face value, sensitive to the neutrino mass. So we have a variety of large-scale structure surveys that you already heard about this morning. In the form of a matter power spectrum, it would look something like this, which again is super impressive. And if you look at the error bars, that would indicate that we can actually measure this matter power spectrum at percent level precision, We also see quite nicely, of course, the baryon acoustic oscillations in a plot like this, even better in a plot like this. And that measurement breaks a lot of the deterrences that we have between parameters in the standard cosmological model, and it also helps to measure neutrino masses. Now, quantifying the effect of neutrino mass on the matter power spectrum, it would look something like this. So this is just a plot showing linear perturbation theory. It's the ratio of matter power in standard lambda CDM, meaning a neutrino mass of 0 lambda CDM, to the actual model with a non-zero neutrino mass. And it's done in such a way that you keep the total matter density the same in the two models, so that basically matter radiation equality happens at the same time, because it makes the plot nicer. It's easier to see the effect of the massive neutrino. And what you should really take away from this is that massive neutrinos have an extremely dramatic effect on structure formation. It's not a small perturbative effect. Even a minute sum of neutrino masses actually has a very, very substantial effect. And it's quite visible. If you look at the error bars that you saw before, we should be able to see neutrino masses of this magnitude. But of course, this also points to one of the problems in this game, namely that you don't measure the neutrino mass directly. You measure it together with a whole bunch of other parameters. And in fact, as you'll see a little bit later, we don't even measure the neutrino mass as such. We measure contributions to the stress energy tensor at various times in the universe. So this mass could be, in fact, from something else, not a neutrino. Okay, in a little bit more detail, for a 0.1 eV neutrino, the suppression plot would look something like this. So it changes as a function of the cosmic scale factor, so as a function of redshift. These colored lines show the full nonlinear ratio plot, so that's not in linear perturbation theory, but using full n-body simulations. And you see these quite nice effects that are very scale dependent, which in principle can also be used to probe the neutrino mass even better. So going to neutrino physics, you saw this plot before already this morning. Of course, there are many, many, many analyses in the literature trying to pinpoint the neutrino mass from cosmological observables going back to even the 90s. And here you see the most recent incarnation of the Planck analysis, which very clearly illustrates that we are now at a level where, at least within the lambda CDM framework, the neutrino mass can be estimated quite precisely, or at least bounded quite precisely. This is yet another table. You've seen several of these analyses already today. So this is showing recent neutrino mass bounds in various hierarchies, so degenerate hierarchy, normal hierarchy, inverted hierarchy. So again, equivalent to what you saw Eleonora showing this morning. And you can also see that formally the mass bound is different in these cases, but that's purely due to the fact that it's a prior volume effect, right? It's because in the inverted hierarchy, you have a much higher lower bound for the neutrino mass. As we'll see a little bit later, cosmology is in fact never sensitive to the exact ordering. It's sensitive to the total contribution to the energy density. So this difference is not really because neutrino mass is directly observable using cosmological data. So this you already saw in a very nice talk this morning. And really the focus of my talk is slightly different. It's really about how to avoid the bound. So the question is, how would one go about fitting in a large neutrino mass? So for example, Massimiliano already mentioned that it could be that Katrin or another experiment has a positive detection of a non-zero neutrino mass. Cosmology measures nothing. So how do you reconcile these two scenarios? Now, going to the basics, if you have a non-zero neutrino mass, what actually happens to cosmology? So first of all, if you have a neutrino mass in the sub-electron volt regime, you modify the matter radiation transition. And that leads, for example, to a change in the Hubble rate around the epoch of recombination. And that clearly has a visible effect on the CMB. It also has an effect on the early ISW effect, so that enhances CMB fluctuations just to the left of the first acoustic peak. And then, of course, neutrinos basically don't cluster below the free streaming length. And that leads to a very substantial reduction, in fact, a very large reduction in matter clustering. And that can be seen through, for example, weak lensing or directly in the matter power spectrum. And that means if you have a large neutrino mass and you want lambda CDM to be compatible with it, say you have a mass which is substantially larger than the current mass bound in simple lambda CDM, then you can go about it two ways, basically. So either you can play with an unmodified neutrino sector, and that means just standard model active neutrinos, but then you have to modify cosmology in some way. And the way you have to modify it is basically to enhance clustering, because neutrino mass lessens clustering. Alternatively, you could play around with neutrino physics and say we could have, was also pointed out by Massimiliano, you could have non-standard interactions, for example, in the neutrino sector. So if we start with category 1, which from the neutrino physics point of view is, of course, by far the simplest, then you could start adding parameters to your cosmological model. You could go beyond the simplest lambda CDM model. You could add a tensor component from inflation. You could add a non-cosmological constant equation of state to the dark energy, and so on and so forth. Now, in the old days, if you go back 15, 20 years, you can in fact completely alleviate the cosmological neutrino mass bound by adding parameters to standard lambda CDM. So you can see an old plot here, which is from the WMAP era, which clearly illustrates that if you go away from the -1.0 that you have for the cosmological constant, and you go to, in this case, a somewhat crazy model, which has phantom behavior, but if you just take it as fitting parameter, you can see that you can very easily alleviate the cosmological mass bound. But over the past decades, data has become far, far better. And that means it's gotten much more difficult to get away with a high neutrino mass. So of course, you saw in Eleonora's talk that you could play around, for example, with this lensing parameter, and you can actually allow for a much larger neutrino mass. But it's gotten substantially less easy to go this way. And that brings me to the other category, which from a neutrino physics point of view, of course, is more interesting. Now, that would be modifying neutrino physics. So for example, one way of doing it would be to make the neutrino mass a dynamical quantity. So for example, you could have mass varying neutrinos. You could couple neutrinos to a scalar field, and you would essentially have a neutrino mass that evolves dynamically in time. You could have spontaneous neutrino mass generation, as in this model by Giardwali and Lina Funke. And if you take it to be a dynamical quantity, you could actually make what I think is a very nice and illustrative analysis from this paper by Lawrence et al., where you can see what is actually the time-dependent mass bound on neutrinos depending on cosmological data. So you can see as a function of redshift. In the early universe, you are severely constrained by the effect on the CMB and also on lensing of the CMB. But if you go to very small redshifts, then it becomes much easier to allow for a high neutrino mass. So if you could somehow dynamically change the neutrino mass at very late times, it certainly would be possible to accommodate a non-zero mass detection by Katrin, say, and cosmology. So that's quite interesting, of course. Alternatively, you could have non-standard neutrino interactions. You could play around, for example, with the prototype non-standard interaction, which would be a Fermi-like new interaction that has been done many times in the literature. And actually, it's quite interesting. So what happens if you have non-standard interactions that are strong? You suppress free streaming of neutrinos at early times, and then free streaming commences once this interaction decouples. And actually, as you can see here in a likelihood plot of the effective strength of this non-standard neutrino interaction, you could actually have quite strongly interacting neutrinos being completely compatible with cosmology. So that's interesting, of course. But would it also allow for a higher neutrino mass? In that case, the answer is no, unfortunately. You can, depending on how many neutrinos you have interacting and whether they are strongly or moderately interacting, you can change the mass bound somewhat, but not substantially. So the Fermi-like interaction is really not probably the way to go if you want to hide a large neutrino mass. Another possibility would be to couple neutrinos to some new light degree of freedom, either scalar or pseudoscalar typically. And that would have very interesting consequences potentially. So if you have coupling of neutrinos to light pseudoscalars, say, that would mean that if you have neutrinos that are massive, they can pair-annihilate quite efficiently even. And well, okay, they can always independently of the mass, but the point is that if this degree of freedom is lighter than the neutrino mass, that would be a way to hide a large neutrino mass because they would simply annihilate away and you would never see the effect on large-scale structures. So that scenario is called the neutrinoless universe and was proposed by John Beacom and collaborators in 2004. Unfortunately, it also has the effect that it suppresses completely free streaming and that leads to unacceptable behavior, unfortunately. So this scenario most likely is not a good way to go about it. But just for illustration, you can see what happens. This is for a sterile neutrino case. But the point is that you could hide a very large neutrino mass by basically annihilating it away and getting the same matter power spectrum as in standard lambda CDM. Whereas normally, if you have a massive neutrino, which is several electron volts, well, you would get this substantial reduction in matter power, and that would be disallowed. Now, okay, so this is basically what I said. Let's skip on to my final point, and that is, so even if we measure a non-zero mass from cosmology, do we even know that we've measured a neutrino? And the point is, of course, we don't, right? Because cosmology is not flavor sensitive if you discount BBN. What cosmology actually measures is the contribution to the late time energy density and the early time energy density quantified in this effective number of degrees of freedom, and then to a very minor degree, the transition from relativistic to non-relativistic in the neutrino sector. And that means that cosmology can't really tell you if what you're seeing is a neutrino mass. And also, more importantly, if you just stick to neutrino physics, you cannot tell the hierarchy from cosmological observables because you have very, very limited sensitivity to the exact transition time. Just for illustration, you can see here, if you were to change neutrinos to be instead a bosonic component and ask how big a difference would that make to large scale structure, this was a calculation that I did with a collaborator a few years ago. So if neutrinos were bosons instead of fermions, but with exactly the same energy density, then you would get minute differences. So really, it's very difficult to say quantitatively specific details about the distribution of neutrinos. What you can say is just what is the current density, what was the density in the early universe, and not much more than that. And that means also if you ask the question of whether cosmology can ever truly probe the hierarchy, the answer, of course, is no, not in the foreseeable future, not even the distant future, probably. So whether cosmology can actually measure the hierarchy depends on what the sum of neutrino masses turns out to be. And essentially, it's just that if the sum of masses is below roughly this value here, you cannot have the inverted hierarchy. But that's not a real detection, of course, one should bear in mind. And that means that it will forever remain important to have direct confirmation of neutrino masses, even though at face value cosmology is so super sensitive. And that brings me to my conclusion, which is that, well, within the standard lambda CDM framework, which may or may not be the correct framework, we don't know that, of course, as you've heard, cosmology has extremely good sensitivity to the neutrino mass. You can change that or alleviate that a little bit in extended models, but really you have to move to models which are a little bit extreme in order to completely remove the current mass bound. Now, on the other hand, if you change neutrino physics, it's certainly possible to accommodate even a very large current neutrino mass in cosmology. That's not a problem. And finally, this caveat that I mentioned, even if we are to measure at some point a non-zero neutrino mass from cosmology, of course, we don't know, strictly speaking, that what we're seeing is a neutrino component. We still need confirmation from direct experiments. Okay, so that's what I had to say.
Thank you very much, Steen, for that an excellent and interesting talk. I want to open the floor for questions. Our first question is from Zoom. Hamish, could you please unmute and ask?
Yeah, thanks for the nice talk, Steen, on this topic. You made a pretty strong statement that cosmology really is only sensitive to the sum of the masses, and that surprised me a bit, because I would have thought that you could have the mass or the inverted ordering and produce a certain mass. And in one case, you have two light species which behave like radiation until quite late. And in the other case, you have only one. And I would have thought that cosmological observations would be sensitive to that difference.
It's a very good point. And of course, this is what you would sort of at first sight expect, right? Because you would think there's a very clear difference in the redshift where you have the transition between relativistic and non-relativistic. After all, the mass is 3 times higher than it happens a factor of 3 earlier. But the point is that we have no real observables in that redshift range. So we have very precise observables going back to a redshift of around 1100. And then we have very precise observables starting at a redshift of a few. But this transition typically happens at a redshift of around 100 or so, where we have absolutely no way of making observations and no real way in the not so distant future of making observations. So unless we had some way of really probing in detail that redshift range, it's very difficult to see that transition, and therefore you are in fact only sensitive to the sum of masses.
Right. Okay, thank you. That's very interesting.
Questions from the room?
Just a follow-up question on that answer. Could you imagine that with really precise measurement of lensing of the CMB, that you could identify structure in the scale of the lensing that would be sensitive, just as a dream theory idea?
In lensing, probably not, because the highest redshift that you have available is in fact the epoch of last scattering. And lensing is mainly sensitive right around the halfway point. That's where you have maximum lensing probability. And that's quite a low redshift. I think what might presumably be possible at some point in the far distant future is to make some 21 centimeter observation that goes to extremely high redshift, because that would be, at least in principle, a way of going to maybe a redshift of 100 or 200 and actually seeing this transition. But here we're talking super duper far future.
Alec, you're next. Could you unmute?
Yeah, thank you for this. I was particularly interested in your final bullet there, that if you see something in cosmology, you don't actually know what it is. And I was curious about 2 things in that context. If we have good reason to believe that neutrinos exist, roughly as we think they do now, how do you get them to not be responsible for what you saw in cosmology, and what else might it be?
Yeah, I mean, I agree. It's quite difficult, actually, because the standard model certainly predicts the presence of a neutrino background. And I think Eleonora also mentioned that that in fact we measure something compatible with the cosmic neutrino background at many sigma significance, probably around 10 or 15 sigma or so currently. And that means it's extremely difficult to build a model which has no neutrinos but some other component. But one way in principle of doing it, of course, is to have neutrinos coupled to some other new light degree of freedom. So in this neutrinoless universe, you could, in principle, at least have the new pseudoscalar degree of freedom having a mass which is somewhat lower than the neutrino mass. And then you would still have this annihilation taking place. And then what you'd measure in the current universe would in fact not be neutrinos, but some other degree of freedom. So certainly it is possible to make these models. They might seem a little bit contrived, but I think it's always a fair point that what cosmology is really measuring is not the same thing, right? It's a contribution to a stress energy tensor, because that's what affects structure formation.
Talia, your question is next.
Thank you. So you talked about this scenario in which perhaps Katrin measures a neutrino mass, which seems to have been ruled out by cosmology with standard lambda CDM. And I appreciate you discussing the different possible changes that could explain that. That was really helpful. I was wondering which of those changes, if any, could at the same time help to resolve the Hubble constant tension?
Oh, yeah, that's pretty difficult, unfortunately. As Eleonora also mentioned, resolving the Hubble tension is not very straightforward, in fact. So many analyses have been done trying to pinpoint where would one have to modify physics in order to resolve everything. And certainly modifications that happen around the epoch of recombination seem to work better than late time modifications, but there are always problems. And I think it's pretty safe to say that we don't know of any neutrino physics scenarios that convincingly solve this tension. So of course, that's not to say that some version of a neutrino physics scenario might do it. It's just that we don't know any scenario that is really compelling in that sense.
That's very helpful. Thank you.
Yeah.
Any other questions from the room? Okay, thank you again, Steen, for an excellent and stimulating talk. So Andre, can you share slides? So our
you
next,
want me to share my slides? I can do that.
yes. And then you can control them.
How about the microphone?
So can someone online tell us if you can hear Andre speak again?
Can you hear me?
Yes.
Yes. Yes. So let me go to full screen.
Yes, as well.
All right, and you can see the little hand here.
Yes.
Yes.
And I can move the slides. Do people in the room mind if I take my mask off, because my glasses will fog up? If somebody minds, just let me know.
Okay, I think
Yes.
I think the record shows it's okay with us.
Okay, thank you. So sorry. Thanks for the invitation, and I'm sorry I wasn't here before the break. So I will probably say things that Jason said before, but hopefully I'll say it differently. He's usually right and I'll be wrong, but just keep that in mind. So my job is to tell you something about model dependency in neutrinoless double beta decay probes, especially when it comes to informing the neutrino mass question. And I'll also talk about some of the things to remember about neutrinoless double beta decay searches in general, and how they inform the Majorana versus Dirac question, and why it's always useful to keep in mind that it would be great if we had lots of other ways of asking if the neutrino is Majorana or Dirac. And we really don't, because double beta decay is great, but it's nice to think about. So just to set the stage, I think it's a very, very big question in neutrino physics today, ever since we discovered that neutrino masses are not zero, that we would like to learn whether the neutrinos are Dirac or Majorana fermions. I think if you ask around to your theory friends, if they had one wish, what would that wish be? And if it had to be a physics wish, you would probably ask if they want to know if the neutrinos are Dirac or Majorana fermions. And if nothing else, if you're in the business of understanding where neutrino masses come from, learning the answer to that question really guides you in very, very different directions when it comes to understanding where neutrino masses come from. Especially if the neutrinos turn out to be Dirac, theorists will be confused. We've already started thinking about it, but it's not what we expect. And you should keep in mind that what we expect doesn't mean it's true. It's just what we expect. And we've been wrong before, so keep that in mind. And of course, the theme of this session is, of course, we would like to learn what the neutrino masses themselves are. And I won't dwell on this too much because that's why you're here. But it's a very important question. You can't get the answer with oscillations. Oscillations don't know how to do that. So you have to appeal to these types of probes that we've heard about in the last several talks, including precision measurements of the kinematics of beta decay, cosmology that we just heard from Steen again, and neutrinoless double beta decay. I think it's important to keep in mind that this is an important question. So it's not just one of those, let's tabulate the numbers and get everything lined up. The answer also guides our understanding of fundamental physics. For example, and again, it's useful to gauge the discussion in terms of what is the value of the lightest neutrino mass, because since we know the differences of the neutrino masses squared, if you know any of the masses, you can find out what the other ones are. So if the lightest of the neutrino masses happens to be 0, that's weird, and it says something. So theoretically, you have to not just explain why the neutrino masses are not 0, but you have to explain that one of them, by the way, is 0. So that's a non-trivial question. On the other end of the spectrum, imagine that the lightest neutrino mass is relatively large. That means that you're in a situation that all of the neutrino masses are sort of degenerate. And again, if you think about this from a theoretical point of view, that means that the mechanism that generates non-zero neutrino masses also has to contain in it some information that says that the masses have to be pretty similar to one another. Of course, all of this gets colored a little bit because we don't know the neutrino mass ordering. And for example, if you've never thought about this, the inverted neutrino mass ordering is pretty weird. Because in the inverted ordering, there are two states that are really quasi-degenerate at the percent level. Okay, and this is something that, if it turns out to be true, I think it's very exciting. And again, for people who like history and particle physics, we've run into states that had almost exactly the same mass. And it turned out to mean something very important. So for example, the pi plus and the pi zero have almost exactly the same mass. And that turned out to be important. I mean, there was an indication of some symmetry that explains that, in some ways, the pi zero and the pi plus are the same particle, except for weird things like electromagnetism. So it's nice to sort of have a sense of where we are today. This is a plot of the neutrino masses themselves as a function of the lightest neutrino mass. On top, it's the normal ordering. In the bottom, it's the inverted ordering. And you see that in the inverted ordering, the two heavy states are really, really quasi-degenerate, certainly in this scale that I'm making the plot. In the inverted ordering, they don't have to be quasi-degenerate. The cosmology bound is indicated with this sort of cheap arrow here. And you can see that even if you take the cosmology bound completely at face value, there is a region of space, even in a normal ordering, where certainly all of the neutrino masses have the same order of magnitude. And you already are in the regime where the two lightest masses have to be almost exactly the same. So there's a lot to be learned here. Of course, I won't give you a review of neutrinoless double beta decay. It is by far the best way that we have to find out if the neutrinos Majorana or Dirac, and it can inform the neutrino mass question. This is a neutrinoless double beta decay has been around for a very long time, and it's going to be around for a very long time in the future as well. The big shift especially for people that are a little bit older, is that because we've discovered that neutrino masses are not zero, neutrino-less double beta decay becomes a qualitatively more informative endeavor, because you're bound to learn something even if you don't make a discovery. And so I do want to emphasize for people who think about neutrino-less double beta decay, my recommendation always is to forget about neutrinos. You're really looking for the violation of a fundamental symmetry. And that's kind of a big deal in its own right. What makes this exciting is that if you do see neutrino-less double beta decay, you learn instantaneously that because lepton number is violated by 2 units, the neutrinos must be Majorana fermions. And that statement can be debated, but I think it's a correct statement. And of course, there's a lot of progress that's been made with experiments. And I'm sure Jason talked a lot about this. We are in the process of starting to cover this inverted ordering region. And this also sets, I guess the other nice thing about the neutrinos having mass is that it does provide you with a stepwise neutrino-less double beta decay program that has concrete goals that you can talk about. So that's the story. So my talk is mostly to explain why you shouldn't be super excited about learning about the neutrino masses themselves from neutrino-less double beta decay, because there are lots of things you need to worry about. And I think the main points I want to make is, of course, if you don't see neutrino-less double, and this is obvious, but it's important to keep in mind, if you don't see neutrino-less double beta decay, it doesn't mean the neutrinos are the Dirac fermions. This falls into the category of you can't prove a negative, which, by the way, is a wrong statement. It's a contradictory statement, because if it were true, then you can prove that negative. But you know what I'm talking about. Of course, you only learn about neutrino masses if the neutrinos turn out to be Majorana fermions. So that's sort of important. And that even counts for the non-observation. So if you rule out the inverted ordering, and you say, aha, now I know that the ordering is normal, that of course is only true if the neutrinos are Majorana fermions. If the neutrinos are Dirac, you have nothing to say about the order. The really important thing that I know Jason touched upon, at least it was on his slides, so I'll take that as something he mentioned, is of course, this is a very model-dependent probe. And I think the story is, non-zero neutrino, or a discovery of neutrino-less double beta decay implies that the neutrinos are Majorana fermions. And the fact that the neutrinos have non-zero masses drives neutrino-less double beta decay. It is by no means guaranteed that that's the dominant contribution to neutrino-less double beta decay. One thing we'll also try to mention is even if the neutrinos are Majorana fermions, there are lots of reasonable scenarios you can write down where their contribution is suppressed or even absent. So the connection between observing neutrino-less double beta decay and the neutrino masses is indirect in a few different ways, and that's what I'll spend most of the time talking about. And of course, I'm not going to talk about the issue of the matrix elements, but if you do make a measurement of the lifetime of neutrino-less double beta decay, in order to properly inform the neutrino masses, you really have to do this translation between the observable and the particle physics number, and that relies on a lot of nuclear physics, and there's a lot of homework that needs to be done. I think my 2 cents on this, since I'm not an expert on this at all, is that it is very exciting that there are lots of interesting developments in the nuclear theory of neutrino-less double beta decay. So there's reason to be optimistic that we will go from this world where we are now, where the error bars are, I think as Vincenzo said, like a factor of 3, we might go down to, let's say, 20%. I'm making this up, but it sounds pretty plausible. And that's exciting. And by the way, the theory efforts are driven by the experimental efforts. The fact that the experiments are there and that there's a promise or there's a hope that you actually make a discovery, that drives the theory community to spend a lot of their resources trying to understand what the answer is. Okay. So I want to make a quick comment that will be important for what I'll say next, which is this infamous funnel region that people are so afraid of, which is right here. And first, I want to remind you of how that happens very quickly. this effective mass to which we're sensitive is actually a complex number. It's the sum of three complex numbers. And if you're adding three complex numbers and they form a triangle in the complex plane, they add up to 0. And if you've never done the exercise, you should. You can quickly convince yourself that in the inverted ordering, it's not possible to make the triangle close. In the normal ordering, it is possible to make the triangle close. And that's exactly what happens here in this funnel region. So that's what's going on. It's a good exercise for undergraduates. Now, I think it's important to keep in mind that we may learn from experiment that we're not there. So that's something that's important to keep in mind, is that if it turns out that we learn from some other probe that the lightest mass is bigger than, let's say, 0.01 electron volts, you cannot be in this funnel region. This cancellation is just not possible. Another point, so I'll keep this picture here. Another point which is important is that depending, if you talk to your theory friends, there are theoretical models that cannot live in this funnel region. A very simple model is one that predicts, for example, that the lightest mass is very small or 0. So if somebody has a scenario that predicts that the lightest neutrino mass is 0, you have to be here. So you can't be in the funnel region. So these are important things to keep in mind. However, if we happen to live there, it's not fine-tuning. And it's important to keep, so what I mean by that is it is very, very easy to construct a scenario where that number vanishes. I think the easiest way to appreciate that is that if you write down the neutrino mass matrix in the flavor bases, this is what the neutrino mass matrix looks like. And one of these elements is called MEE, which is exactly M beta beta. They are the same thing. Sometimes people call it MEE, maybe not for that reason, but that's what it is. So what you're basically asking is it possible that this entry of the mass matrix in the flavor basis vanishes? And the answer is absolutely. And if you construct, for example, a mass model where you also try to explain why is the electron mass so small, it could be that this number has something to do with the electron mass. And it would be a lot smaller than the other numbers. Okay, so I think that's also important to keep in mind. And there are scenarios where these things tend to happen without you asking for them. So it's not like you're designing the model to make MEE equal 0. There are circumstances where this just happens. And again, I don't want to discourage people by saying that there's a whole lot of models that say that MEE is 0. But again, it is possible that we live in a world that looks like that. So just keep that in mind. And there's nothing we can do about it. But just something to sort of keep in mind. I want to give you a very quick example of new physics where the neutrinos are Majorana fermions. They're actually very Majorana fermions, whatever that means. And you still end up having no rate for neutrinoless double beta decay. And that's the seesaw model that everybody likes. That's the one everybody knows about. So if you take the seesaw model, you're adding to your standard model Lagrangian right-handed neutrinos. The right-handed neutrinos are allowed to have Majorana masses of their own. You get this very nice Lagrangian. After electroweak symmetry breaking, all of the neutrinos get Majorana masses, including the neutrinos we know about. And these right-handed neutrinos that sometimes we call stereoneutrinos, sometimes we call neutral heavy leptons. It depends on who's talking and what the masses are. But that's a good scenario. It says that there are lots of neutrinos, let's say 6, because you can pick how many right-handed neutrinos you like. So if we add 3, then we have these 6 neutrinos. And of course, we can fit the data with the parameters we have at hand, which are the Yukawa coupling and the right-handed neutrino mass. It turns out that this is a very, very efficient model for giving neutrinos a mass and fitting all the data, in the sense that whatever you want the right-handed neutrino masses to be, you can fit the data. Except if the neutrino masses are in this region between 10 to minus 9 electron volts and about 1 electron volt. The reason this is ruled out, it's ruled out by oscillations. So if you did have a very light stereoneutrino, these, by the way, have a huge mixing angle, then in that scenario, you would have seen the stereoneutrinos by now. So we ruled that out. Everything else is allowed. And of course, we like to talk about a very, very high scale seesaw model. And that's where the mass is, this is in electron volts. This is like 10 to the 24 electron volts. So it's actually off my chart by a factor of 2. So all of this is allowed. By the way, if it's too large, it's not allowed because the Yukawa coupling is non-perturbative. But that's the only bound that we really have. So we have a lot of room to explore. And one point that I like to drive home is that we really have no idea what this mass has to be. And the reason is this mass is not related to electric symmetry breaking, for example. It's a brand new mass parameter now, Lagrangian. It is protected, so it doesn't even get perturbative large corrections, for example. So we're stuck with having to figure out what this number is supposed to be. If this number is small, this is just a cartoon of how things could look like. You could have a bunch of new masses that are in the, let's say, 10 electron volt range. That's completely fine. If you want one of these guys to be the dark matter, sure, you pick that to be around a keV. You have to work hard to make it be the dark matter because it doesn't work very well, but you get the picture. So these guys could also be very light, and they would show up in things like a tritium beta decay because they would be stereoneutrinos. They could show up in oscillations. And by the way, they would contribute to neutrino double beta decay, which is what we're talking about. But they do that in a very annoying way for you. So again, if all these new neutrinos are light, they all contribute to MEE or to M beta beta. And they do that just like everybody else. So you have 6 neutrinos, you combine all of them. If you do that, so here's the contribution from the light neutrinos. Here's a contribution from the heavy neutrinos. If you do the calculation very carefully, this sum is exactly 0. Okay? And why is that? Because you have now a 6x6 mass matrix. And again, MEE still means MEE. It's the EE entry of your 6x6 mass matrix, which is exactly 0, because that's, you put it in, it's 0. So you don't have a choice. And by the way, in this scenario, any other observable that even if you change the flavors around, it will also not allow you to discover lepton number violation in this way, because your active sector doesn't have, this is all in many quotes, but your active sector doesn't have lepton number violation. The lepton number violation comes in the mixture with the stereo sector, but because all of your states are very light, there's no distinction between them. So you can kind of throw away the stereo states. You only have the active states. They don't know about lepton number violation. There's no lepton number violation that you can observe. But all my fermions are Majorana fermions, and they all have completely different masses. Again, this is a specific scenario. If you start making the right-handed neutrino masses heavy, life changes, and your effective mass can turn on. So as you make, so this is as a function of, let's say you take the heaviest of these guys and you start making it heavier, at some point, it doesn't contribute just like everybody else. And once you remove that complex number from your sum, then the sum no longer vanishes. So that's just something that's well known, and it was pointed out quite a long time ago. And people have done detailed studies of this. So I just, and again, I claim that this is my job for this talk. I don't think you should be discouraged by the fact that there's one particular model in one range of the parameter space where this vanishes, but it is important to keep that in mind. And I should say, of course, that there are stereoneutrino models where they do contribute to neutrinoless double beta decay, although you should be careful whether those models are completely self-consistent, and they usually are not. They're just sort of an ad hoc stereoneutrino model. And you always have to ask, where is the stereoneutrino? How does it contribute to neutrino masses? What else is contributing? So you have to ask a bunch of questions. So I stole this from Vincenzo's talk yesterday. And of course, the other thing which is very important about neutrinoless double beta decay is, of course, there are other contributions depending on how lepton number gets broken. So if you have other new physics that violates lepton number, it also contributes to neutrinoless double beta decay in a way that doesn't have to be directly related to the neutrino masses. There are lots of examples of that. So in Vincenzo's slide, he told us about left-right models where you have a right-handed W and a right-handed neutrino that can drive neutrinoless double beta decay in a way that you can constrain. What I want to spend a little bit of time, and this is the last thing I'll talk about, is instead of giving you a big list of models, I think it's useful to think about this in a context of neutrino masses. And the reason I want to gauge it that way is whatever new physics you put in that will give you neutrino-less double beta decay will be lepton number violating physics. Again, that's the story that you're telling. So that physics will contribute to neutrino masses. Okay, it doesn't have to do it in quotes directly. It can take a long time for that information to percolate to the light neutrinos in the quantum mechanical sense. It could be that your model forbids Majorana neutrino masses at the 3 level, but quantum mechanical corrections or loops are going to give you a non-zero neutrino mass. And we all are aware of this. This is important. You know, we construct neutrino mass models that are designed to do that. So it's interesting to ask, so if I construct mass models that know how to do that, how much does that change neutrino-less double beta decay? So again, if I just have an ad hoc model that violates lepton number, I can make it contribute to neutrino-less double beta decay by whatever amount I want. I think it's informative to ask, if I combine that information with the neutrino masses, do I learn anything interesting? So again, this sounded confusing to me, so hopefully it wasn't confusing to you. The idea is to ask are there neutrino mass models where what you're learning from neutrino-less double beta decay is not just the light neutrino contribution, and does neutrino-less double beta decay inform your origin of the neutrino masses in an interesting way? I think that's kind of what I want to say. And I don't want to dwell on this too much because I have no idea how much time I have. So there are ways of gauging these models by looking at higher dimensional operators that also violate lepton number. So for people who are not in this kind of business, what we're really doing is talking about a model of models. So this is a mechanism that captures some of the low energy manifestations of some UV complete model by higher dimensional operators. And we try to use the higher dimensional operators to understand what are the different consequences of this model. So the way that this works for people who have heard about it before is that you say, I have some new physics at the UV, I integrate it out at the 3 level, and I get some higher dimensional operator that violates lepton number. And then I ask the question, how does that generate a non-zero neutrino mass at the loop level? And you can do an estimate of that by doing a loop calculation that only includes standard model particles. So hopefully that made sense for those who are paying attention. Okay, so that's the idea. And there are lots of models that violate lepton number by 2 units. They have to be odd dimensional. So lots of operators that violate lepton number by 2 units. They have to be odd dimensional. Another fun exercise that you can do, and you can write a paper about it if you want. It's a consequence of the quantum numbers of the fermions and the particles in the standard model. So here's a set of all this is a dimension 5 operator that everybody knows about. There's a whole bunch of dimension 7 operators here, and then a bigger bunch of dimension 9 operators. So all of these operators violate lepton number by 2 units. So if I have new physics, then when I integrate it out, I get this operator at the 3 level, and I don't get any lower dimensional operator at the 3 level. I can then generate neutrino masses at the loop level involving standard model particles. And I can use that to, for example, gauge what's the physics scale of this operator. Okay, so that's the story. The reason I'm talking about this is that if you pick one of these operators like a O14b, it's an operator that looks like this. You notice that this is the neutrino-less double beta decay operator at the quark level. So that means that this physics knows how to do neutrino-less double beta decay at the 3 level. And by the way, it does neutrino masses at the 2 loop level. So that's kind of an interesting claim that you can make. And by the way, if you like other lepton number violating observables like mu-3+ conversion in nuclei, it knows how to do that as well. So that means that this is a scenario where you would be tempted to believe that you can do neutrino-less double beta decay much better than you can do neutrino masses. There's an extra wrinkle in this story, which is the neutrino masses are still very small. It doesn't matter if they're happening at the 2 loop level or the 1 loop level or the 3 level. So the neutrino masses are telling you that the effective scale of this operator has to be at a certain size. And that sometimes it screws up the dominance of this 3-level contribution to neutrinoless double beta decay. Okay, so I'm not gonna, so this is what's explained here. I'm gonna skip this part. So we made this very long chart that includes lots of information. The one we want to concentrate on, these are the different operators. The gray region is where the neutrino masses want the scale of the operator to be. And the blue bars with an arrow in them are the constraints from neutrinoless double beta decay today. And you see that, not surprisingly, most of the time, the constraint from neutrinoless double beta decay tells you that the scale of the operator is not such that the neutrino masses are very large. That's something we already know, because we know neutrinoless double beta decay doesn't like the neutrino masses to be 1 electron volt, or whatever the bound is, right? So
That's a point of clarification. In those cases, you're assuming that that operator is dominating.
absolutely, that is the only contribution, that is the dominant contribution to neutrino masses.
A question about the data on this. You're
Yeah.
using the most aggressive matrix element for that
Uh,
one? Is that the bottom of the Camelin set?
Yeah, that's so this paper is older than the most recent
okay.
Camelin set. Fortunately, everything scales like lambda to some power, like 4. So it
width of the bar.
it doesn't matter.
Okay.
I mean, it's not true that it doesn't matter, but this is mostly for illustrative purposes. But yes, this is a good question. And matrix elements will make everything fuzzier, but not in a way that it overwhelms the plot. And and the message is there are some places, for example, like here in this model O4b, there's no neutrinoless double beta decay bound. Why? Because MEE is 0 in this model. Why is MEE 0? It's because of the symmetric structure of the operator that has to be anti-symmetric. So in order for you to get a non-zero neutrino mass, you have to take something that's anti-symmetric and it gets converted into something symmetric. Long story short, MEE turns out to be 0. So that's here are the dimension 9 operators. Here you have the opposite case. So you have this model 07, which is ruled out by a neutrinoless double beta decay. So if this model were the origin of neutrino masses, we should have seen neutrinoless double beta decay a long time ago. This happens for a couple of other models. These are scenarios where this 3-level contribution to neutrinoless double beta decay is overwhelming. By the way, the 09 operators usually generate masses, the dimension 9 operators usually generate neutrino masses at the 2-loop level. Not always, but pretty frequently. So that's kind of the landscape says that, and I don't want to talk about this too much. My favorite operator is this OS. This is an operator that violates lepton number by 2 units, but it's really, really bad at generating neutrino masses because there are no lepton doublets in the operator at all. It's called the singlets operator. So in order to generate a non-zero neutrino mass, you need a lot of Yukawa couplings. That makes the contribution so small that we would have seen this physics in like LEP or even before that. So it's totally ruled out. But the strength, so there are some cases where double beta decay has a lot to say. So again, this is sort of a summary of all these different plots. This gives you a sense of where the new physics scale could be. And for all of these operators, we expect neutrinoless double beta decay to say something very important. And it may just be that the neutrino mass contribution is dominant, but there are plenty of good neutrino mass models where you get a non-trivial contribution to neutrinoless double beta decay. And if you got this contribution there, it would hint towards a direction that the neutrino masses could be generated in this interesting way. And again, I won't talk about this because there's a whole talk about how do we learn more. The way that we learn more is by making more measurements of the neutrino mass and hoping that we don't fall on the bar, right? And I'm sure there was I looked at the slides for the talk before the break, and I'm sure a lot of it is to convince people that, hey, if we landed up here, which is not possible because of the current bounds, but if we landed like here, then we would know that neutrinos are Majorana fermions, and we would know that the neutrino mass exchange mechanism is not the dominant mechanism, and we would have a lot more work to do. And I presume that's what that talk was partially about, because I wasn't here. Okay, so let me just conclude. It is very, very clear that if you want to learn about whether neutrinos are Majorana or Dirac, you have to do neutrinoless double beta decay searches. Okay, however, you're not guaranteed to make a discovery even if the neutrinos are Majorana fermions. So we should keep that in mind. That could happen because of flavor. It could happen because the new physics doesn't allow you to make a discovery. So for that, my propaganda slide out of this is that it is very important to try to think about other ways of asking if the neutrinos Majorana or Dirac. We've done a little bit of work on this. I think mu-3 conversion is probably second best on this list of how to look for a lepton number violation in a very generic way, but it's very, very far away from neutrinoless double beta decay. By the way, if you're curious, in these plots, the line which I didn't talk about is where the mu-3 conversion sits. And you see that they're always to the far left of saying something interesting, unless you find the right model where something exciting happens. Again, searches for neutrinoless double beta decay can provide non-trivial information on neutrino masses. However, of course, the connection is very indirect. It's always fun to remind yourselves that neutrinoless double beta decay has nothing to do with neutrinos. Actually, it's in the name. It's neutrinoless. We really don't want the neutrinos to be there. So keep that in mind. And of course, I think once we make a discovery and get a Nobel Prize, the next big challenge will be to probe very deeply what is this connection between non-zero neutrino masses and neutrinoless double beta decays. And again, as we've been discussing in this session, the other probes for neutrino masses are the real place to go in order to see if you get a concordance measurement of these different ways of seeing the neutrino masses and asking if they are. And finally, I want to leave you with a very important question, which is, and what if the neutrinos are Dirac? So how do we learn anything? And like I said, we can't learn that they're Dirac by not seeing double beta decay. By the way, we haven't seen it yet, so we should be done. But by not seeing it, even if you can cover the normal ordering region, it will be very plausible to believe that the neutrinos are Dirac, but it won't be a proof. And it may not be possible to get a proof, but it's always something to keep in the back of your mind, right? If you could come up with some way that says, hey, here's evidence other than that I didn't see neutrinoless double beta decay, that the neutrinos are Dirac, that would be kind of amazing. And there are a couple of things in the air that we can start thinking about for the far future, like measurements of the cosmic neutrino background. And I think, but it's a great problem to keep in mind. So let me stop.
So thank you very much, Andre. I think we've gone a little bit into the general discussion, but I think we should start with a discussion of your slides. So I'd like to open for questions.
Yeah, two related questions, I think, and I missed the early part of your turn to talk on this. I'm sorry. Is it not the case that if we knew the mass was in the inverted ordering and we didn't see double beta decay, that we would know they were Dirac? I'm missing a loophole there.
That's the part of the talk that you missed.
Okay. And my second point is, so there was a paper, boy, 20 years ago or something, I don't remember, Langnecker maybe, I forget who it was, saying you'll never measure the CP phases.
Yes.
And so the question is that really, the papers like that are right for a while and then they come wrong?
Yeah, so there are a couple of papers on that. I think it's fair to say that any credible observable that you can come up with for the foreseeable future has no hope of seeing the CP phases. That would be my position on this.
Bottom line, why?
The effects are just super tiny. And remember, all the effects that we get are these combined effects. So I think that is the answer. It's not the best of answers. So basically, you'd have to be in. So let's do the best case scenario. Imagine that cosmology sees something, a tritium beta decay sees something. We get a great number for these two effective masses. Even though they don't necessarily have to be the same thing, we plow on and we try to reconstruct as much information as we can. We do double beta decay. How well do you want to know the matrix elements? Is it 1%, 0.1%? So I think that's the challenge, that you really have to be in a world where you can claim that you know the neutrino masses themselves very, very well, and that you've seen lepton number violation without this gigantic cloud of the matrix element. That's probably makes it.
That's why we do experiments. We're supposed to be good at that. We're just supposed to suck that up.
Okay, so I can give you the futuristic theorist version of this. There is an old paper that we wrote a long time ago, which is fun. But what happens is you can measure neutrino, anti-neutrino oscillations. That's another way of looking for it if the neutrinos Majorana or Dirac.
Right.
Good luck with that.
Yeah.
If you could measure that, you could actually measure CP violation in that. And that's proportional to the Majorana phase.
Oh, that's interesting.
So that's the best example I know of the Majorana phases actually doing what you expect a phase to do, which is to violate CP.
Is it not the case in, say, pion decay or something that you get you know,
Yeah, that's
you
a
get
good, so the,
super
yeah.
rare process, you know. You're
well,
looking
yeah,
at
that's right. So
18.
again, let's take neutrino double beta decay. And how do you look for CP violation there? You actually have to look for anti-neutrino double beta decay, and that means that you have to have an anti-nucleus. So let's say you do that.
Suck that up. Yeah. That sounds kind of hard.
Even if you do that one, you have to ask then, are the rates for neutrino double beta decay and the rates for anti-neutrino double beta decay the same? And they might end up being the same even if CP is violated because of things like the CPT theorem. So it's hard. So that's why these oscillations are a great place to look for CP violation, because of it's very clean, so it's easy to explain to people. And you are doing this CP violation in decay, and all that you need are different contributions to the amplitude. And if they happen to have the same magnitude, the CP violating effects are quite large, which is what happens in ordinary neutrino oscillations. So that was a very long answer. Sorry.
So I want to invite the folks in the hallway. We have chairs up here and we promise not to bite. So yes, Julieta.
Building on that, my question was also about the CP violating phases. Are there, do models make specific predictions for CP violating phases? I imagine the answer is yes.
Yeah.
And then the other question I had is, does double positron decay get you anything that double beta decay doesn't get you?
So the first answer is yes. So there are models that have things to say about CP violation and these CP phases. And again, it's the relative complex entries of your mass matrix. Not all models do that. Many models don't do that. So it really is, there are classes of models that people get excited about because there are models that have a non-trivial thing to say about CP violation. And those models have been certainly well explored for what we call the Dirac CP phase. I am going out on a limb a little bit, and I can claim that they probably have something to say about the Majorana phases as well, because the CP symmetry is entwined with the flavor symmetries that you're inventing. So, and Lisa's there, and she can correct me if I said something wrong, but I think it sounds right. Now, the other one, the short answer is I don't think so, but I don't know. And that's, of course, to look for the nuclei that are decaying from the other end. I don't see any obvious, huge complementary thing that you're learning, but I'm happy to be wrong. I haven't thought about this enough. It's a good question.
Jason.
Earlier in your talk, you mentioned how there's a real qualitative difference from the theory perspective between having a Lidus mass equals 0 versus just being less than the splittings.
Yeah.
Experimentally, those are indistinguishable. And actually the window is kind of running out on being able to make the distinction between those two cases. I wonder if you could comment a bit more on those scenarios.
Yeah.
How important it is to measure the Lidus mass if possible.
So it's very important. So we would like to know the neutrino masses as well as we can. It's a very difficult thing to do, clearly, for everybody in this room that we know all about that. And you're right, it's impossible to measure 0. I think that's even true. So the best you can do is to start telling people, hey, the Lidus mass is pretty small. So that means we're in this part of the plot here. Right? And the way this would work is that, let's say that you convince yourself that the Lidus mass has to be a factor of 10 lighter than the second Lidus mass, or factor of 50 lighter, and then a factor of 100 lighter, that's when people will start to concentrate on identifying this as something to pay attention, something interesting. So basically, if the lightest mass is 3 times lighter than the second lightest mass, this sounds kind of boring. That it sounds like when I say boring, it sounds as if there's really not a lot of information we will extract from this fact. But once you start getting that the masses are hierarchical, by a 1 to 10 or 1 to 100, and in the super duper future, if you could say that, hey, this mass ordering is bigger than the electron muon mass difference, which is a pretty big gap, then you're starting to believe that this means something important. And I agree with you completely. You will never be able to tell us that the mass is 0. But I think once the numbers start to be big gap, then it will be very tempting to concentrate on scenarios where the lightest mass is 0. And by the way, the seesaw model is a very simple way of telling you that the lightest mass is 0. If you only have 2 right-handed neutrinos, there's not enough room in your matrix to give everybody a mass. So it's a very natural consequence of the minimalistic seesaw model where you only have 2 states. And by the way, that's another model that's falsifiable because you make a lot of other predictions that have nothing to do with what we're talking about.
Yes. Can I ask just a follow-on question? Because I really like the way you put it there, Andre. But so, did we learn something fundamental from the fact that the quark masses span many orders of magnitude?
That's a great question. We've been puzzled by that for a very long time.
It's almost like you plot it on a linear, plot all this mass on a linear scale.
Absolutely, yeah.
The top quark is crazy on a log scale.
Well, so if you ask your theory friends, they'll tell you that the top quark is fine, everybody else is crazy. But this is guided by completely unfounded prejudice. So I do want you to keep that in mind. Having a model for the Yukawa sector of the Standard Model, forget about neutrinos, is something we have not done successfully. And we have lots of models. Many of those are great models. They fit all the data really well, but we have no idea which one is correct. But it is a big question because it could be very important. And but we don't know because all the information we have are these numbers that have these patterns to them. And it could be really important, but we really don't know yet. And some people have dedicated a lot of their research careers to just understanding that. And they had very fruitful research careers. Other people will throw their hands up and say, I have no idea. Let's not worry about this as a physics problem. And I think the jury is still out. If you could travel to the future 200 years, you could ask that question and they'll say, oh, you're stupid. Of course. Or of course, this is not a good question. It might be like, why do the planets have the distance to the sun that they do? And we found out eventually that turned out to be not a super fruitful question to ask. But smart people thought about it, and they were smarter than me for sure. So.
Jason.
Another comment you made early on is that the inverted ordering is very interesting because of how, these 2 degenerate states. In the next round of double beta decay experiments, we'll be exploring for the normal ordering, the region where that's happening for the lower 2 states. Is that interesting in the same way? I think it's interesting in a very similar way. And again, this is also in the realm of trying to understand where these matrices are coming from and what the mass is. So yeah, so if you're here, you're basically in a position to say that the 2 lightest states have a non-zero mass and they're quasi-degenerate. Again, quasi-degenerate is always it's a trigger, right? 2 things why would these states be exactly the same mass? That makes no sense. So that calls for an explanation, which could be, deeply embedded in the mechanism behind non-zero neutrino masses. I think the same is true, by the way, of things like, what if theta 2,3 is exactly maximal? That's another weird thing. Nothing is exactly something, right? So it's the same with these almost exactly degenerate states. People like these types of models in terms of generating neutrino masses because this smells like undergraduate quantum mechanics that you teach your students. Imagine you have it's a 3-level system, but at leading order 2 of the levels are degenerate, and then you add a perturbation and then they break up. So that's exactly the model that you have in mind. It doesn't matter if this happens for the heaviest, for your excited state or for your ground state.
it matters a little bit because the breaking is a little bit different, but that's the logic here. And people like, and this was something people were already excited about when we could live up here, because that would be a scenario where all the masses are almost degenerate. And isn't that interesting, right? You know, could you have a situation then where your mass matrix is perfectly diagonal, and then you perturb it, and then that generates everything? That, by the way, is also a good way of getting large mixing angles, because the perturbation can, you know, to the when you break your degenerate levels, you all remember in the graduate quantum mechanics, right? So it's the same math. It's exactly the same. So there are all kinds of fun things like that. So absolutely, this is a great point. And I think, yeah, if we're here, it probably means something interesting. Again, we call the normal ordering normal, and normal really means this, right? This is normal. This is not normal. This is definitely not normal. So that's inverted. Yeah.
That's good. Can you talk about what you could do if, let's say, you took away all the experimental challenges and were able to measure the cosmic neutrino background?
Yeah. So the point which is associated with this, which is very interesting and very important, is if you could measure the cosmic neutrino background, and if you convince yourself that you know the flux of neutrinos here very well, which we claim we do already today at the, let's say, 5% level, 10% level, depends on who you ask. You know, neutrinos don't clump very much, so we don't expect that effect to be a big effect. So if you know that, and if you measure the cosmic neutrino background with a 50% error bar, you can tell if the neutrinos are Majorana or Dirac, because the rate is different by a factor of 2. So it's a factor of 2 effect, big effect, super big. So it's kind of like, you know, the solar neutrino problem. A factor of 3, even the home stake experiment could see it in the 60s. Okay, so this would be a factor of 2 effect. And this would be a kind of amazing if we could do that.
If they're not Majorana, is there a new bar asymmetry? Not that we can see.
Right, so I'm counting on the fact that the new bar asymmetry is small. So that's the caveat there. So you could try to live in a world where then there are no new bars.
Right.
Then that would screw this up. Now it's
crazy, no?
It's completely crazy. I think we would know about this already. You know,
Okay.
we know we've done a lot of cosmology, and it would be difficult to come up with a model that allows for that asymmetry. And again, keep in mind, you know, that the neutrinos were in thermal equilibrium. We're very sure about that. You can't be in thermal equilibrium and have a chemical potential of infinity, right? You can, but then you need a lot of new interactions and stuff that are taking care of that. And that's probably really hard to live with. There are constraints on the lepton asymmetry. We know the baryon asymmetry is very small. The lepton asymmetry can be way bigger, but it's still at the, I'll make something up, but it's still at the percent level. It can't be bigger. This lepton asymmetry is known not to be bigger than, this is from data from Big Bang nucleosynthesis. If you mix in mixing, the whatever applies to the electron neutrinos applies to the other flavors as well. So that number can't really be bigger than some percent.
Unless it happens after nucleosynthesis, if there was some. sort of-
Absolutely, yeah. So, but then you're asking a big question. So what is this physics
Yeah, absolutely.
that's making all my antineutrinos disappear that I don't know about?
We all still didn't see it, yeah.
Yeah, so that's the challenge. I'm sure you can come up with one, but it's also probably completely ruled out by everything we, you know, cosmic surveys and things like that. It's a weird physics, right? How can this physics make all the antineutrinos disappear in a way that we don't see any of the side effects of that, or we don't see this physics doing something completely different in the laboratory? I'm making all of this up. I haven't thought about it, but it sounds implausible to believe that you can come up with something.
Could you measure the Majorana phases?
With
If you measure through
the cosmic neutrino background?
Yeah.
I don't think so.
Well, I guess the question is there a prediction?
I think
Well,
the
if
answer is
there is a
no.
prediction for
Yeah.
what that-
No, the answer is I'm sure the answer is safely no, because you have this incoherent mixture of mass eigenstates. So you're really just measuring the new 1 contribution, the new 2 contribution, and the new 3 contribution to this. And I'm imagining you're doing Ptolemy or something like that. So you're measuring just the scattering of the new 1, new 2, and new 3 it is definitely not going to be coherent. That means you're not sensitive to any phases. You're only sensitive to the entries of the of the mixing matrix, which are your couplings, but you're not measuring any interference. So you don't have any, you can't even measure delta if you want. It's a good question. I would, again, Majorana phases are still phases. They still have to show up in interference. That's not negotiable. So you need to come up with some observable that sees different amplitudes that can interfere with one another. And I think the ways in which we envision measuring the neutrino background don't have that information.
Yeah, I was just trying to imagine if you had an experiment that did that produced an electron, compared it to a different one that produced a positron. That might be just.
No, that wouldn't work because you're just measuring the couplings, the absolute value of the coupling square. So to be fair, if you calculated this at like the loop level, you could do it. So if you do it at the loop level, it is possible to get a different rate, and that would be CP violating. And I don't know how the Majorana phases would show up there, but it is probably not true that there's probably no Majorana phases because you're not measuring a scattering. Okay, I have to think about that. I'll think of that.
I might take this chance to try and steer us back toward neutrino mass. Is your question on neutrino mass?
Sort of? I don't know.
I don't see any neutrino mass related questions on Zoom or in the room, so maybe we'll transition to a general discussion. So I think first, I really want to thank all the speakers who have blown me away, and I'm sure Luis as well with what we expected. This has been amazing. I think one question that I really wanted to bring up here is that all three of these probes are kind of operating in a regime where we're all measuring zero to pretty good precision. And I know that the neutrinoless double beta decay community has put a lot of thought into what would it take for an observation of neutrinoless double beta decay to be believed, because there have been reported observations that are not believed. So this is something that a lot of effort has been invested in. So I think I would like to hear people's opinions, maybe starting with cosmology. If we suppose that, the next generation measures a neutrino mass scale that's significantly non-zero, but let's imagine that the Hubble tension still exists and there's still some details in the lensing amplitude that seem to be inconsistent. What would it take to be confident about that limit? I wonder if anyone would like to weigh in.
Sorry, did you say a measurement of the neutrino mass or?
Sorry, the cosmological observable, the sum of the three neutrino mass values. If we imagine that that's, say, 4.5 sigma away from zero or something, then do we believe that? Or
maybe I can try a first dance with the answering Max talking. Yeah, so there are I think several avenues here, because there are, let's start from far, there are several reasons why we might doubt measurement of neutrino masses from cosmology, as we have heard. So one is model dependency. Okay, so model dependency can be, let's say, beat to some extent in two ways. So one is just trying to explore the largest possible number of models. No, but that of course is kind of a it's a never-ending task, no? In the sense you can always think that there is some other crazy model that fits the data, giving you a zero neutrino mass, so giving you a different number. Still, it's a good, let's say, brute force strategy, especially if you somehow try not to go to two crazy models. I know this is kind of a vague answer, but I would that's a first strategy. Another strategy is to look for different probes, because when we say cosmology, the situation here is different. No, it's not like a single kind of experiment or of observation. So we have the CMB, The CMB itself might mean many things. We have primary anisotropies, secondary anisotropies. We can use kinetic Sunyaev-Zeldovich to measure the radionization optical depth, which somehow enters into your determination of neutrino masses. So you have different data combination. If you look at the forecast paper for the Simons Observatory, actually they quote numbers, they quote sensitivities on sigma, on mu for different combination of probes inside Simons Observatory, which is an experiment that is looking just at the CMB, at the damping tail, at the high L's of the CMB. And of course, the situation becomes better if you also start putting into the mix measurements of large-scale structures and so on. So another way of beating model dependency is to look for consistency, okay, between data combinations, because of course, when you start having inconsistency, you might start thinking that you're fitting things with the wrong model, okay? So that's that's the first half of the answer. Second half is that another reason why you might not believe cosmology is because of instrumental systematics. Okay, so for example, foreground removal and this kind of stuff. And I think that even there, the answer is always the same. Try to look at as many observables as possible, and this will allow you to get robust constraints. That said, my opinion is that you can get as robust as you want from cosmology, but we really want to look to get a measurement from kinematic measurements, okay? Okay, so depends what you mean with what do you need to believe. In some sense, you should never believe that. No, I think also Steen was very clear about that. We are not really measuring the mass, we're measuring their contribution to the stress energy tensor, and I completely agree with the statement, obviously. So that's my take on that.
Thank you. That sounded to me as a non-cosmologist very comprehensive and clear. Does anyone want to
follow-up question maybe for this group, which is if you had a cosmology measurement of neutrino mass, would that change how you run the experiments in any way? If you knew what you were targeting that specifically, would you go to say a weaker source so that you could collect more statistics with lower systematics at some specific, value of data, right? Like, would it change anything about the way the experiments are run, or is it always just getting more sensitivity?
Sorry, I don't know whether I got the question. Can you say that again? Sorry.
Do you mind repeating it?
Yeah, so I'll repeat it. So I think that the question is, if a cosmological experiment makes a non-zero measurement of the neutrino mass scale, would that change anything about the way that additional cosmological?
No, sorry, I mean kinematic experiments.
Oh, I'm sorry.
Yeah.
Okay.
So it's kind of a question for people who do kinematics.
Okay.
If you knew exactly what value you were looking for,
right,
would you change anything about the experiment?
So would you use the cosmological input?
Yeah.
To
design a slightly different experiment that you might otherwise do?
I think Brent would like to respond.
Well, if I can talk without being committal about it.
Yeah.
If someone told me that the neutrino mass was 1 eV right now,
well,
okay.
Let's not use 1
half
eV.
an eV.
Yeah.
Maybe Project 8, for instance, doesn't need to use atomic tritium anymore. That's a really different experiment. That's an easier experiment, I think. We would at least do an intermediate stage targeting that, I would guess.
Yeah, I mean more if we go in the next generation of CMB experiments. So not within the already excluded CMB region. If you learned it was 100 milli eV, does that change anything about the experiments?
That does not change anything. 100 milli eV, we're in the range where we have to use atomic tritium. Project 8 is how it's got to be already at that level.
I think the challenges from Holmium would be the same challenges that, that we anticipate. Maybe that leads us to, kind of, maybe we should direct to the kinematic community. We've talked a lot about the model dependence that should make us all more skeptical about cosmological or neutrinoless double beta decay, constraints on the neutrino mass scale. if a kinematic measurement, and let's pick Katrin because Katrin's sensitivity range is in an awkward place for the indirect probe. So if Katrin makes a significantly non-zero discovery of the neutrino mass, what would it take for you to believe that? Would it need a confirmation by a separate experiment? Would it need a separate isotope or a different method? What would it take for you to believe that type of result?
So I'll say this, if Katrin makes a very significant non-zero discovery, then Project 8 could be in the regime where you don't necessarily need to use atomic tritium. That would cause us to do an intermediate phase.
Right, and Project 8 would be ready, you say.
I'm not going to make a committal statement.
Okay.
It'd be a lot easier than it might have had to be.
Jason.
So I mean, I guess you know, the definitive structure in the beta decay measurement is the kink, right? But I believe that in Katrin, you know, with the energy resolution, and I think a lot of the strength in the measurement is coming just from the rate suppression. And so, yeah, I guess I would want to see how well those systematics on the rate suppression are really known, and is that really a real suppression that's being seen?
Sure.
So can I direct this question to the Katrin people? So, I mean, if you did make a discovery tomorrow, what are the knobs that you have to turn in order to convince yourselves that you've actually made a discovery and not that you've screwed something up? Are there, I am sure that there are knobs you can turn, you know, to make the signal go away, to make, you know, to do those sanity checks that I hope people have spent a lot of time thinking about.
So I might be the designated person here. I think one very obvious and straightforward knob is just to, you know, say like seal that data set, or, you know, publish that data set and then start a new completely independent data set and make sure that you have a separate set of statistics. In terms of sanity checks for the systematics, one nice one is extracting the endpoint of the spectrum, which is a free fit parameter for Katrin. This is a free fit parameter because you know, determining the actual absolute experimental energy scale is complicated at that, you know, it's very tiny, the deltas that you would need to look for, and measuring the mass difference between the tritium parent and the helium-3 daughter is also difficult, right? But if you can improve, so right now we can do cross checks between the current measurement and the Katrin measurement, and they're not extremely precise, but they're precise enough that their agreement is very encouraging. And I think that in the event of a positive signal, that's something that we would definitely want to push on to double check that we are recovering an endpoint that is consistent with atomic physics and with our understanding of the apparatus. I think that one other important thing to note is, you know, of course, Katrin is always pushing very hard on systematics, but because you're measuring the spectrum in a very steeply falling region, if there's a systematic effect that you haven't accounted for, it tends to make the neutrino mass squared value that you extract more negative. Because if you imagine some random systematic that just you know, misassigns events between energy bins, there's a lot more statistics in the lower energy bins than the higher energy bins. So it's going to go one way preferentially, and that tends to shift you toward a negative neutrino mass squared value, or it would make a positive neutrino mass squared value look like 0 instead of erroneously giving you a positive measurement. Josh.
Is it like double banded here, but for different reasons? Is there value in a different nucleus, like some Fano factor that could be systematically wrong that we have, or some nuclear effect that causes the endpoint to be distorted in some way, and therefore you say, well, if you saw it in holmium or whatever, you know, pick your isotope, then you got the same mass, you would feel a lot better about it.
So for tritium is a super allowed decay. So the nuclear physics is very simple. One thing that holmium gets you that we haven't discussed yet is that in holmium electron capture decay, you're emitting a neutrino and not an antineutrino. That would be nice to confirm that those masses are the same. We expect them to be the same. It would be nice. Jason.
I'm wondering how realistic the scenario we're discussing is, where Katrin would see a significant non-zero neutrino mass. There's a small window for that, and the sensitivity of Katrin is order of a few hundred EV, but that's the typical upper limit sort of sensitivity. So one thing we've done in the double beta decay community to focus on discovery is talk about discovery sensitivity, and I wonder, does Katrin actually have the discovery sensitivity for this type of scenario?
Right, so that's a good question. I should say that we have sensitivity, including discovery sensitivity numbers from before we started running, and we calculated a discovery. So our upper limit sensitivity target is 0.2 EV, which is very famous. The discovery sensitivity that corresponds to that is 0.35 EV. So there's still room above that. We're working on updated sensitivity calculations. Of course, we have a lot more experience running the experiment now, but that's a work in process.
Just a quick question. What's the discoveries? What are you using for discovery? Using free sigma?
I will have to get back to you on that.
Curiosity.
No, it's a good question. All right, Alec.
Yeah, I was curious about something that relates both the discovery sensitivity and also the question of the kink. I was curious, for each experiment, we can presumably define a math scale at which the kink would be visible in that experiment, right? It comes up mostly, given our current reach, in sterile searches for things that are much heavier, which I think gives us a clue of where that scale would be for any of the current experiments. But in terms of a really convincing discovery, I agree that seeing the kink, or three kinks, ideally, would be fantastic, right? And so maybe we should quote an additional parameter, which is, for this experiment, how heavy does the something have to be to see at least one kink in the results of this kinematics experiment? And maybe that's grounds, say Katrin measures something but can't see the kink, you come back with a super high resolution atomic tritium experiment that can see the kink at that fairly large level in comparison to the standard sensitivity of the atomic experiment. Maybe that would be interesting.
I think that is interesting, and I think that it's not really something that the kinematic searches have thought very deeply or intensely about, just because we know from oscillations that the energy resolution that you need to see these kinks for the active flavors you need a very punishing energy resolution. But thinking in the blue sky, that would be very nice.
And I
Josh.
mentioned one blue sky ideas, which goes back at least 20 years, people talking about in terms of neutrino mass, is, as you all know, from your helicity suppression question that you had as a PhD student, that it's the lightness of the neutrino that fixed helicity gets you the wrong helicity for the electron. Of course, the neutrino does have mass. And so the question is, how many ion decays, for example, it's like something like 10 feet, just the same. But how many pion decays, and how well could you actually resolve helicity on the charged lepton without screwing it up? I could tell you about neutrino mass. And back when we thought about this, yeah, I see. It sounded really hard. Number one, you can't really do like Stern-Gerlach on a. You need longitudinal Stern-Gerlach essentially to get the helicity, which is hard. On electron, it's even harder because there's like actual quantum mechanics levels. But it might not be impossible. And with PIP2 and all these gigantic proton beams, you could get a crap load of pions. Okay. And so if anybody wants to think about it, their hands, I don't know that it's impossible, but it is a completely different way. It's a rare process experiment. I need the one guy who's got the wrong helicity, one charge left on that has the wrong helicity. So it's not as impossible as maybe it's only just 10 impossible. 10 to 18. Yeah, exactly. 10 to 18, but not 10 to 20.
Okay. interesting idea. Yes.
So there is one more observable which has connections to like the neutrino mass scale or its Dirac or Majorana nature, and that is the neutrino magnetic moment. And that is also something that we can constrain either from laboratory measurements or like red giant bounds or astrophysical bounds. So like based on the current constraints on the neutrino magnetic moment and near future or far future constraints, how much can we learn about neutrino mass and nature of neutrinos, which is degenerate to or complementary to what we can learn from all the other probes?
I mean, I can add one sentence to that, which is there was a very nice paper. Again, the neutrino magnetic moment in the standard model is expected to be super tiny. So you need new physics. But there's a generic study you can do. Actually, Vincenzo might have been in that study, right? With Peter Fogel and yeah, so he can talk about that. I will not quote him because I'll do it wrong.
No, it's again, it's the magic of quantum mechanics, right? So if you assume that there is a magnetic moment, and you're emitting to the quantum mechanics and gauge invariance, you have to do it with electroweak boson, so you can close the loop this, and it generates a neutrino mass, right? So at the loop level, the one loop level, and therefore, again, here's where the argument becomes a little fuzzy. You require that the contribution of the neutrino mass is smaller than, let's say, 1 eV. That's what we used 15 years ago, and therefore you get a strong bound on how large magnetic moment. And so the study was, yeah, I think for Dirac, and there's a distinction for Dirac versus Majorana. For Dirac neutrino, we found that in units of the Bohr magnet, and this was 10 to the minus 14 Bohr magnet, which is few orders of magnitude smaller than the astrophysical bound. And I was part of that project, but then there was a branching project, a follow-up project where they studied other people, I mean, some co-authors, they studied the Majorana case. In the Majorana, I can't quite remember. I think the idea is the same. I can't quite remember the number, but it was close. It could be larger.
Yeah,
much larger. It could be larger. It was close to the current bound, just minus 11. So one could argue that, yeah, there's a window there, but if you see a magnetic moment, you learn something about the nature of the material. So that I should say, I mean, when I said this fuzziness of the argument is this, it's a naturalness argument, right? So you're assuming that the quantum evolution from the scale to the observable scale is not cancelled by some initial condition. It could be, right? That it's cancelled by some initial condition at high scale, and so all this argument goes away, right? So so you're assuming that there's nothing funny going on at high scale, cancelling that. So this kind of argument has come a little bit into question with called the Higgs mass and the electroweak scale. So take that with a grain of salt. That's what I'm trying to say. But I think it's a robust quantum mechanical argument.
I think if we're talking about alternative neutrino mass probes, there is an indirect kinematic method from neighborhood supernovae, right? That you can look for the dispersion of neutrinos that arrive in the burst from the supernova. My understanding is, I think there's a limit of around 5.5 eV from supernova 1987A. Right. So we could do better on that, on the timing, and we'll do better by a lot on the statistics. But my understanding is that at a certain point you run into some systematic limitations from your understanding of the dynamics of how the neutrinos are emitted. I'm not an expert.
Well, I mean, that's where, let me say two things.
Yep.
So one, that's where complementary detections help. The flavor and anti-flavor. I think that helps you get, you can see, or mirror of the stellar dynamics. Not that it would be for free, somebody have to figure out how it works. Secondly, the other thing that makes me nervous is, in some cases, depending on how close the supernova is, some of the detectors in all-site don't have the timing to do it unless they have a huge number of statistics.
Mhm.
Right? I mean, you're talking photon system, it might be at best 30 nanoseconds, it might be like 100 nanoseconds.
Mhm.
Okay, so that's a short time anyway, so it's pretty nearby supernova, but still, it seems like kind of a waste not to get nanoseconds, like 1 nanosecond when you're trying to do this. So,
Mhm.
And that's where the liquid simulator.
yeah, that's right. That
Those are
would be a
1
big
nanosecond
plus.
or better.
Why do you say 30 nanoseconds?
Just because you got the propagation down the files. So at the very least, that's 30, and then you have the rise time of the symbol, you have the bouncing of the photon inside the outer. So
That adds to 30
yeah,
nanoseconds. That seems like a long time scale.
No, I think
naively.
30 nanoseconds is aggressive. I think you look at the performance papers.
Okay, do we have any further comments or questions to close this discussion out? A couple of minutes. All right, I think many questions have been answered and many questions have been raised. I want to thank all the speakers and all the participants. This has been really, really informative and educational. So thank you.
Thanks, everybody. Bye.
Bye.